the talk so that it can be later. And for those for whom the permission will not is not there, so we will stop the recording at that point of time. One suggestion or one request is that please mute yourself at all times. And during the Q&A, please feel free to unmute yourself and ask questions. And in fact, Yuhao and myself will be monitoring the chat window. So if there are any questions in the chat window, we'll be happy to put it forward to the speaker. And we'll be taking the question and answers at the end of the speaker presentation. So without further delay, let me first get to session 1, which is on algorithms and applications. And our first speaker is Professor Qi Zhu from Northwestern University. So while I'm introducing him, Professor Zhu, if you can kindly share your screen. Yeah.
All right.
Okay, so Professor Zhu is the Associate Professor at the EC Department in Northwestern University. He has received a lot of awards, best papers, as well as the NSF career. And his research interests include design automation for cyber-physical systems, Internet of Things, system-on-chip design with applications in domains such as connected and autonomous vehicles. And today he'll be presenting an interesting talk on robust and safe machine learning in autonomous systems.
All right, thanks for the introduction, Priya. Yeah, so today I'll give a fairly sort of high-level overview of the work we have been doing in the last few years. In this area, we're trying to ensure robustness and the safety of autonomous systems, especially considering the considering the behavior of neural network-based components. So I'll start with some of the high-level sort of challenges of autonomous systems, especially our use connected and autonomous vehicles, or CAVs, as an example. Now, in these types of systems, the autonomous system will operate within a physical environment and try to sense and perceive the environment via typically learning-based algorithms, especially neural network-based, and then apply planning and control navigation algorithms. Those algorithms will be implemented on a cyber platform. Now, some of the major challenges in those systems, for instance, they are operating in a highly dynamic environment. The functional complexity has been increasing drastically, both due to the increasing of the system features, scale, but also the adoption of machine learning techniques. On the architecture side, the complexity has also been rising with the usage of more advanced CPUs, GPUs, and in the vehicle case, there's also a fundamental shift from the traditional federated architecture to the more integrated architecture, where there's more sharing and contention among software components. And on top of those, there are a variety of strict system requirements on safety, timing behavior, robustness, reliability, etc. Now, a lot of those challenges, we feel like fundamentally they're due to the a variety of different types of uncertainties and disturbances in your system. For instance, the inputs themselves from the environment is highly uncertain. You may have noise in your sensing components. And then you could have very advanced neural networks being used for definitely now for perception and increasingly for planning and control components as well. And for those, due to our current limitation of analyzing the behavior of such neural network-based components, there's also a certain degree of uncertainty as well. And then you may have actuation noise. Then during the execution of the software and on the hardware platform, there may be disturbances in their operation in terms of transient errors and the timing violations, etc. Now, then in the case of this communication among different agents, for instance, between different vehicles or between vehicles and infrastructures, there could be a disturbance to those communication as well, which also added to the challenges in analyzing system behavior. Now, given the time, today I'll only focus very briefly actually on on the uncertainty due to the perception and the planning and the control component, especially in terms of using neural network-based techniques. And in particular, if we look at sensing and the perception part, at a very high level, it can be abstracted as, right, we take the raw data as input and we try to estimate the system state. And here the problem we have been focused on is how can we sort of quantitatively and formally analyze the system's robustness against adversarial attacks on the input. And mathematically, this can be abstracted as an output range analysis problem of the neural networks. And then the planning and the control, the problem is then giving our state estimation, right? How do we ensure that if we are going to use a neural network for decision making for planning and control, how can we ensure the system safety? So I'll briefly talk about both of them. We'll start with the sensing and the perception part. Now, on the perception neural network, there has been a lot of studies on adversarial attacks where, right, the idea is giving a small perturbation to the neural network input. In some cases, it can lead to a very drastic difference in terms of the perception result. So in the seminal work almost 10 years ago now, the researchers have demonstrated, right, when you add a small noise to the input picture, even though to the human eye it looks almost identical, but in the perception result, it could be quite different. In all those cases, will be identified as ostrich, which is not desirable. Now, our interest in this problem is we want to know, when giving such small perturbation in the input, right, how much the output change it can actually lead to. Can we bound such output? Now, this is the so-called output range analysis problem of neural networks. And in particular, at the beginning, we are looking at so-called local robustness problem. So giving one particular input value, input space, we are interested in learning when small perturbation is giving around, right, this input, how much what will be the range of the output value. And this can be formalized as giving a neural network and the compact input set X, typically around a particular input. We want to compute the output Y, or at least have over approximated bound of it. Now, this problem has been studied in the literature in the last several years. A variety of approaches have been proposed. For instance, you can use a fairly efficient interval relaxation method, basically try to approximate each activation function, nonlinear activation function in this case, with the input and output bounds. So basically, very intuitively, you can think of this as approximating the activation function as sort of rectangle. And then if you want to make this more accurate, right, you could try to use so-called LP relaxation. Basically, in this case, use left and right derivatives to obtain a polytope around the activation function, which can give you a more accurate approximation. And then there's also further approximation, further more accurate approximation you can do by, for instance, divide the input interval of the activation function into multiple segments. And then for each of that, you can use a polytope to approximate. So very sort of natural sort of that. And once you are able to approximate each of those activation functions, then you can, from the input, right, all the way conduct your analysis to the output to try to bound the output range. Now, so what we found in our study was, for our purpose for output range analysis, we found that in many cases the direct using interval relaxation may not be accurate enough, and so we are looking into using MLP relaxation, but then the key here is try to reduce the complexity. So there are a couple of approaches, so a number of sort of techniques we have been using. Due to the time, I won't go into any of the details, but some of the main ideas there is to, for instance, try to figure out what's the sliding window we need to look at from each neuron, how far ahead we need to look at, how do we identify the neurons that are most important to apply those MLP relaxation rather than the LP relaxation. So those are some of the ideas. And this work was published about 2 years ago. And so back then, it showed a significant improvement over the state of the art in terms of both the accuracy of the output range analysis and also a slower runtime increase when we increase the neural network size. So back then, we were able to handle input neural network size sort of up to around maybe 10,000 neurons, smaller size of some of the CFA networks. And which is in many of the practical applications may still not be enough. So there's ongoing work in our group trying to further improve the efficiency of that. And there's also, I should mention, there are also recent work over the last couple of years on this problem that has been further, be able to improve the efficiency of such local robustness analysis. We also looked into sort of the application of those techniques in practical applications. One of the problem in particular we were looking at was if we do apply those attacks on autonomous vehicle, how much we may be able to sort of analyze the impact of those adversarial attacks. Now, the key idea here is a lot of the work in the literature focus on the impact of adversarial attacks only on the perception result. But what we felt was it's very important to actually apply an end-to-end approach to really analyze, quantitatively analyze how the inaccuracy in the perception result will eventually affect the system safety. So that was the, the goal of this work we published last year in Intelligent Vehicles Symposium, where we quantitatively try to sort of analyze the impact of adversarial attack on a particular autonomous driving application called automated lane centering, and analyze how much eventually it will affect system safety and whether we can mitigate such attacks. Another problem we looked at very recently was on so-called global robustness. As I mentioned before, the problem we were looking at was on the EMCF paper 2 years ago was for given input, right? And with a small disturbance, how much the output will change. The result of that, if we want to use it to analyze the system safety, especially in a closed loop manner, it's actually not easy to use because of the limitation of the efficiency of the current local robustness analyze technique. It's very difficult to use it in a loop, closed loop manner because you have to call it many, many times. For either for runtime or either for online or offline case, it was quite challenging. So one other problem that motivated us to think about another problem is so-called global robustness. In global robustness, what we are looking at is for any input in the input domain, right? If we apply a certain disturbance with a certain bound, can we analyze or bound what's the maximum disturbance neural network may have in the worst case across all those input space? Right? And this problem, another way of seeing it is how much your state estimation error could be for the entire input space when giving a small disturbance within a bound. And if we can know this, then we may be able to decouple the robustness analysis problem on the perception neural network and the safety verification of your planning and control. So that's what we did very recently, and we proposed an approach based on building these types of twin network and combined with LP relaxation. All right, for the second part of the problem, I'll go through very briefly, is let's say we have a state estimation from your perception neural network, maybe with some robustness analysis. Now, how do we analyze the safety of planning and the control components? And we started with typical traditional model-based controller, but in the recent years, we more focused on neural network-based planning and control. Those neural networks may be obtained through reinforcement learning, imitation learning, right, etc. And the problem of safety verification of a neural network-based control system can be formalized as a reachability problem, basically starting from a certain initial state or set of initial states in a system. We want to know whether the system, typically within a finite horizon, whether it can reach a certain target set, right, without hitting any of the unsafe states as defined. The key in this problem with respect to neural network-based analysis is how can we sort of approximate the neural network-based controller and then connect it with safety verification tools that in the literature. So we had this idea a couple of years ago of using bursting polynomial to approximate the entire neural network controller. And given the time, I won't go into the details. But the result was actually quite promising. We found that compared to some of the other approaches in the literature, we were able to formally prove the safety of a number of cases that were previously not verifiable. And so based on that work, we tried a few ways to further improve its efficiency because that has been the bottleneck. One is on the engineering side. We try to parallelize it on GPUs with partition-based method. This was one work published in 2020. And then very recently, I don't have a slide here, we have another approach where we combine the bursting polynomial with Taylor models. There's a new tool just being released called Polar, and we have a paper on arXiv. You can, if you're interested, you can search for it. And that further improves the efficiency of our reaching and start tool by orders of magnitude, and compared to other tools, also much faster. All right, the last thing I want to mention is then based on those works on trying to formally verify the robustness and safety of neural network-based components, we further look into during system operation, right? They often need to apply certain adaptation. Now, this could be switching across different controllers. This could be changing the sampling period of certain controllers or making other small changes. Now, we are interested in how can we do this with a safety guarantee. So there's a number of works we published over the last 2-3 years of how to do that. And very recently, we're also looking into in terms of learning, right? How can we learn neural network-based controller with a safety guarantee to begin with? All right, so I very quickly go through some of the work. I think this is more like overview of what we have been working on. So if you are interested, you're very welcome to follow up. And I mostly talk about our work on perception and planning and control uncertainty, how to address them. We have also done some work on how do we formally sort of model the disturbance to software hardware execution, and how do we analyze their impact on system safety. And how do we sort of analyze the communication disturbance, especially for connected vehicle applications as well. And so those are some of the papers. Thank you very much.
Ho sentito, vieni. Non sono...
Oh, thank you, Key, for that presentation. Maybe we have time for one question if anybody in the audience has any question. So maybe like I had like a very overarching question here, very interesting. How do you like kind of, because you're coming up with these measures of verifiable safety and verifiable robustness with the feedback in the loop mechanism. So how do you ensure like the universality? Like, because every time there are some new kinds of adversarial attacks coming up, or like, you know, the safety fails that are being proposed every every year there is some different kind of a safety fail that you see for neural networks. So like, is there something like that you can talk about in terms of the universality of this kind of safety verification techniques against different forms of attacks?
Yeah, thank you. I think that's a great question. I think part of the work, the reason we try to formalize, let me just pick this slide. To try to formalize this as a more rigorous mathematical problem is try to make it a bit more general, right? And so many of the adversarial attacks, regardless of how you may generate the attack, the question is if there is a way, right, to bound sort of the input disturbance, then our approach will be able to tell you how much your output sort of state estimation error could be. Now, although there are two challenges here. One is, right, how to actually bound the input disturbance. I think our idea here is there should be some kind of monitoring mechanism in your system to assess how much the input disturbance is. And once within that disturbance, our approach can tell you, right, maybe it's guaranteed to be robust and safe. Once outside of the range, then right, you have to have other ways, maybe go to some backup configuration or switch your perception module or control module. There's another problem I should mention. For the input perception, the robustness problem is only part of the reason, right, for your state estimation error. The perception algorithm itself also includes inaccuracy, right? Mm-hmm. That's yet another by itself a very challenging problem, and we started some work there as well. I mean, there's a lot of recent work on how do we address, right, out of distribution samples and all that stuff. And I think the entire problem is quite complex with all kind of different uncertainty. But I think if we really are interested in, right, prove guarantee certain level of assurance, then we have to sort of try to tackle it in this more rigorous way and also in a more sort of unified way, I think.
Great, thank you so much.
Thank you.
Let's thank our speaker, and maybe we can move on to our next speaker. Our next speaker is Yuan Tian. Dr. Tian is an assistant professor of computer science at the University of Virginia. He has, before joining UVA, he has worked in different firms like Microsoft Research, Facebook, and Samsung Research. His interests involve security and privacy, as well as interactions with computer systems and human-computer interaction. And today he'll be giving a talk on Crypt GPU, basically fast privacy preserving machine learning on the GPU. Dr. Tian, please go ahead and share your screen.
Hi, everyone. So thanks, Priya, for the introduction. Let me share my screen. So today I want to talk about our paper published in Auckland 2021. So Crypt GPU, this is the first secure multi-party commutation protocol fully implemented on the GPU. This is joint work with Sujun, Brian, and David. The reason why I want to talk about this paper is that we are from the security community. So we try to explore how to use hardware solutions to improve the performance of privacy preserving machine learning. And it will be great to get the feedback from the computer hardware architecture about what can we do for the co-design of these two very important schemes. Yeah, thanks everyone for coming. So privacy is really critical for machine learning applications, especially in the high-stake domains. So for example, in healthcare, for privacy preserving inferences, multiple hospitals want to train a critical model for disease diagnosis, and there's a patient who holds a sensitive medical image and want to determine what disease he or she has. The patient can send the medical image to the machine learning model, and the machine learning model can output the inference. To make sure this is privacy preserving, we have two requirements. The first is that the hospitals should not learn about the patient's medical data. The second is that the patient should not learn the weight of the machine learning models. We have similar requirements for training, but training is much more computationally intensive, mostly because of extra backpropagation process to update the model, and also the input data processing in batches. Both privacy preserving training and inference can be achieved by a crypto technique called secure multi-party commutation. For example, several parties can try to train a model together. And also when the data comes up for the inference, it can also be secretly shared into multiple parties and get inference. There has been many constructions in recent years However, this algorithm still won't scale to large data sets and models. In the third model, we consider three-party semi-honest security with honest majority. Well, honest majority means that in the three parties, we allow single semi-honest party for corruption. And what we mean by semi-honest is that the corrupted party will still follow the protocol, but try to gather information out of the protocol. As I just mentioned, the current scalability is the biggest challenge for privacy-preserving machine learning. For example, now it's really, really fast to train LSTM model on tiny ImageNet. But when it comes to privacy-preserving machine learning, especially for secure multi-party computations, the state-of-the-art algorithm in PAT 2021 takes around 1 year to train such a model with such a data set. So the cost of privacy is almost 1,000 times. So as you can tell, that modern deep learning in plain text without privacy is already going to the modern era. But we are still not here yet for privacy-preserving machine learning. And one thing we observe that in plain text training, GPU is really critical for large networks and also model large data sets. But in the privacy-preserving machine learning, what we observe is that, so for the state-of-the-art algorithm, 98% of the training time actually comes from the linear layers. So we are thinking, since scalability is still the biggest challenge for privacy-preserving machine learning, a linear layer is the main performance bottleneck, then GPU can significantly accelerate computations on linear layers. Then we are thinking, okay, we also need GPU accelerations for privacy-preserving machine learning, just as we need that for the plain text machine learning. As a result, we built CryptGPU, the first secure multi-party computation framework, where all computations are performed on the GPU. This work has several contributions. First, we built a system that supports end-to-end private training and inference on the GPU. Second, we build new abstractions and protocols to embed multi-party computation operations on the GPU. Finally, we also run systematic evaluations of GPU-based MPC protocols. Our CryptGPU framework is built on top of PyTorch and Crypt10. So that means it's transparent to the machine learning researchers and engineers. You can just use CryptGPU for privacy-preserving machine learning as if you are using PyTorch. We get significant performance improvement. On private inference, we get up to 3.7 times improvement. And for private training, we get up to 36 times improvement. So now let me tell you a bit more information regarding our system design about how we achieved such improvement. For the system design, we have 3 pillars. The first pillar is that we embed integer operations into CUDA library. So the reason why we need to convert integer operations with floating point arithmetic is that GPU is highly optimized for floating point operations. But for secure multi-party computation, these crypto algorithms always operate on integer operations. As a result, we need to find an efficient and accurate way of doing such conversions. And we use 2 features to finish this. So the first feature is that we can do exact computation for small values. So that means for 64-bit floating point value, we have 52 bits of precision. So that means for integer A and B in the range of -2 to the 26, 2 to the 26, then we can represent them as floating point values and do calculations accurately. The second feature we use is bilinearity, which means that we can convert the products of large integers into the sum of products of small integers. So for our protocol, we actually operate on the 2 to the 64 ring. So that means we need 64 bits of integers. So this directly generalized to operations on metrics. In reality, we actually convert them into 64 bits into four 16 bits groups to do the calculation. So we built CUDA long tensor module to handle such operations. The second pillar is we use replicated secret sharing as basic building blocks. So replicated secret sharing is a kind of additive secret sharing. So you can tell that for each value, it will be converted into 3 pieces of secret shares. And for replicated secret sharing, we use 2 out of 3 secret shares. Each party will hold 2 pieces of secret out of all the 3. So this can easily support addition and multiplications. So for example, here I demonstrate how a multiplication can be done in replicated secret sharing. So you can tell that each party can do calculations on themselves, and with some communications, they will be able to combine the results together in the end. So the third pillar is that we also need to build GPU-friendly protocols for nonlinear operations. So as you can tell, with the first 2 pillars, we can already handle the linear operations accurately and efficiently in the GPU, but we still would need GPU-friendly protocols for the nonlinear operations. It's an example of a convolutional neural network, which we actually also work as experiments for the convolutional neural networks. And here I will tell you some examples about how we handle these nonlinear operations here. So the design principle for GPU-friendly secure multi-party computation is that we need to utilize what GPU is good at. So GPU is highly optimized for parallel processing of simple operations. So that means component-wise operations like matrix addition and multiplication are fast. But operations with lots of conditional statements are slow. And that means we also, if we are using one GPU, then we have restricted memories on the GPU and also memory overload for cross multiplications. As a result, we need to design protocols that are highly parallelizable and less memory consumption. That means classical methods such as gobble circuit won't be a good fit because of high memory consumption and heavy conditional statements. So this makes them difficult to parallelize. Next, I'll give you some examples about how we handle the nonlinear operations. And for this page, I will talk about how we use shared conversion approaches to do private comparisons. And the private comparison is really useful to evaluate a ReLU function. So we know that our mystic share are suitable for linear operations, such as convolutions and matrix multiplications. But for operations such as comparison, private comparisons, the binary shares will be more suitable. We therefore need protocols to convert between arithmetic shares and binary shares. So the conversion typically involves computing a binary addition circuit. So on the right side, you can see that private comparisons is equivalent to the most significant bit extraction. So for example, if we want to compare the value of x and y, we can just try to first compute x minus y, and then trying to get the sign bit, the most significant bit, to know whether it's positive or negative. So that means like with what we can do is that with the shared conversion protocol, we can evaluate private comparison by first convert our mystic share to binary share, and second use bit shifting to extract the Boolean share on most significant bit. And third, convert the most significant bit back to arithmetic share. Since we only need addition circuit, and also it only involves AND or OR gates, then these are highly parallelizable. As a result, private ReLU for our protocol is 10 times faster on the GPU compared on the CPU. Next, I will also talk about how we approximate some functions like explanation. So the explanation is the essential component for softmax function. Before applying the softmax function, we typically subtract the maximum value from the input vector. so that the input will be bounded below 0. And the input function, and we observe from our experiment that most input are between -45 to 0. A standard operation shown on the left side is to use degree m Taylor approximation function to approximate explanation. So the Taylor method can provide a good estimation in an interval of ON, but it diverges as x approaches -infinity. Based on our inputs, it actually requires around 45 rounds to obtain a good approximation. While on the right side, we have the limit-based approach, which can provide a good estimation in the interval O square root n, and does not diverge as x approaches -infinity, and can converge in only 9 rounds. We therefore choose to use the limit-based approach as our approximation function for the explanation. With this approximation function, explanation is reduced to a sequence of element-wise multiplication, which is also highly parallelizable and suited for GPU accelerations. So these are 2 examples. There will be more details about how we handle each layer in our paper. So next, let's move on to our evaluation part. So we run experiments on 3 co-located AWS instances, and we measure both communication and computation cost. But here we focus mostly on the computation cost because that's where the Crypt GPU can help the algorithm most. First, let's look into our benchmarks for private inference. So you can tell that we can support ResNet 152 model on ImageNet and compare to state-of-the-art CryptoFlow, which we published in Auckland 2020, we need around 25 seconds. So it's 2.5 speed up. And for the inference on VGG16 models on ImageNet, we only need 2.3 seconds, which is 3.7 times speed up. And if we do batch inference, the performance will even be much better. So basically, these are the results on the inference. And we also look into the training part. So our training shows that we can train ASPLOS model on 10 ImageNet. Now, instead of around 1 year, we only need 9 days. We also have some macro benchmarks done. So for example, private convolution, which is linear operation, is 100 times faster on the GPU. And private ReLU is 10 times faster on the GPU. And we show that for the privacy-preserving machine learning, we get very similar results as the results of accuracy as the plain text machine learning. For the inference accuracy, we get same inference accuracy compared to plain text inference, unlike for top 1 accuracy and top 5 accuracy. And for the training accuracy, this is just one example because we only ran it for 1 epoch, but you can see that they get comparable training accuracy compared to the plain text learning as well. So this is a moment finally towards the modern machine learning for privacy-preserving machine learning. But there's still a very long way to go as we can, ASPLOS model is back in 2012, and there are many more larger model and larger data set for us to support, especially for the privacy-preserving training set. So we demonstrated the possibility to to build a secure multi-parsing computation framework fully on the GPU. And the interesting point is that when we move from plain text plain text machine learning from CPU to GPU, we get up to 44 times speed up. And when we move that to we move privacy-preserving machine learning from CPU to GPU, we get up to 37 times speed up. So our results is actually demonstrate we build a system that supports end-to-end privacy-preserving training and inference on the GPU, and we improve the performance significantly. And we demonstrate GPU can significantly accelerate on computation bottlenecks for privacy-preserving machine learning. Currently, Crypt GPU also incorporates into Facebook privacy-preserving framework Crypt 10, and our code is also publicly available here. Okay, so I want to suggest that GPU acceleration is really critical for scalable privacy-preserving machine learning, and developing GPU-friendly cryptography, or maybe designing specific hardware accelerations for secure multi-party computation will be essential for achieving this. Thank you very much.
Thank you so much, Yuan, for that wonderful talk. We do have time for one question. Somebody has raised a hand. Please go ahead.
Thank you. Thank you for the talk. I was just wondering if have you looked into if you take a GPU with some number of cores and change to some other number of cores within and see what the effect would be. Have you any comment or any experiment on that? Thank you.
That's a good question. We actually didn't try that. So we only did experiments on CUDA, and also so the experiment results I have shown the most important ones. But we do have some macro benchmarks that might be helpful. As we actually, and I actually also want to get feedback from the hardware community, because we are just trying to make it work and trying to choose the most efficient protocol based on our understanding. But any suggestion will be really helpful about how we can further improve this using other hardware features. Yeah.
Okay. Yeah. Thank you.
Thank you. Yeah.
Thank you, Yuan. Thank you so much again. And in case there are any questions in the chat, please feel free to answer them on the chat.
Okay. Yeah, thank you.
Thank you so much. So moving on, our third speaker and the last speaker of this session is Dr. Emre Nefzi. He is a professor. He's an associate professor in the Department of Cognitive Sciences and Computer Science at the University of California, Irvine. And since July of 2021, he is also an institute director at the Jülich Research Center in Germany. His current research explores the bridges between neuroscience and machine learning, with focus on theoretical and computational modeling of algorithms best suited for neuromorphic hardware. And today he'll be presenting a talk on neuromorphic hardware for robust and safe learning at the edge. Emre, please go ahead.
Yes, can you hear me?
Yes.
Okay, great. So I'm sharing right now. How's this look? Looks good? Okay. All right, so thank you very much, Priya, for the introduction and inviting me here. So I'm going to talk to you about something a little bit different from the two previous talks, namely neuromorphic hardware and how we can use it for robust and safe learning at the edge. So one of my research goals is really to understand how we as humans can ingest information and build generalizations on top of this and implement these on hardware. And so this figure here is an example of Josh Tenenbaum's group showing how, so if I give you three examples here of these objects, which are unknown, presumably called tufas, you can identify pretty easily the other objects. So just based on these three images, you've actually built a generalization in your mind of what that object is. And this is something that a classical neural network cannot achieve on its own. And so I think this gives us some food for thought on the way that we train our neural networks, and in some way the incompatibility of the way we train our neural networks with this kind of behavior. And in fact, if you look at early deep learning, a lot of early deep learning was really learning from zero. So you build a convolutional neural network with weights drawn at random. Of course, there's some structure here that's maybe inspired from the brain, but it's largely learning from scratch, whether it's in reinforcement learning and classification and so on. But this is really not how we as humans and also animals learn. So in fact, really based on this really little amount of knowledge, we're capable of building powerful generalizations and abstractions. And how we achieve this is still largely a mystery, but there's a couple of theories that are out there. And this is also something that we, of course, notice in children. So we notice how our children, they learn through these landmarks, and there's some interesting work also going on there in trying to bring this landmark-based learning to machine learning as well from this group at Facebook. what I really want to emphasize here is that we as humans, and animals in general, we adapt we modify existing knowledge. We don't start from zero. And the same is true for even the microscopic animals. So this comes from a really interesting book of Principles of Neural Design by Sterling and Lofton. So they make this really nice introduction on how these small, so E. coli or C. elegans, they're extremely small, but yet they do have some adapting learning capabilities that, interestingly, are adapted to exactly the kind of interactions they are expected to have in their environments. So in some ways, they do have learning capabilities, but a lot of the behavior is predetermined genetically. And their behavior, as I said, so it scales pretty closely with the size of the animal itself. So again, here, this is an example where their brains essentially just they adapt to exactly what they need in order to survive. And this idea is coming in the latest years. You don't really see so much of deep learning starting from scratch. Every time you want to apply deep learning into a practical task, you actually start from a pre-existing model. And you can look at some of the models that are out there. There's actually very few that start from scratch. A lot of them are actually based on some form of transfer learning. So we'd really like to build this idea into our neuromorphic systems, and ideally even also build systems that can learn online by interacting with the real world. Okay, so starting with this idea, so we want to build now these systems that can learn online, and we would also like to build some knowledge to it. It's really a good idea to do this, because if you don't do it, well, if you try to learn neural networks from scratch, firstly, you need to have a lot of data, and you need to have this data presented in a very special fashion, in a very non-biologically incompatible fashion. And if you don't do this, you get all sorts of problems such as catastrophic forgetting. For instance, if you're trying to train a network to learn MNIST, if you only show zeros and then ones and then twos, by the time you arrive at nines, the network would have forgotten what a zero is. And this is also something that humans perform much better than computers. And also, real world learning can be very slow, because real world means real time and only one data sample at a time. So it is really a good idea to have this starting point for a neural network rather than training it from scratch. But we also don't want to learn on the hardware from scratch. So a solution to this is what is now being called bi-level optimization. So it's really, in some ways, it's trying to replicate this idea that brains learns in stages, and also we'd also like to have something similar in our hardware. So we essentially choose I'm drawing this very hand-wavily in this figure, but one basically landmark stage here, in which we'd say, okay, we would like to pre-train the model up to this stage, and the rest, which is basically the last mile, we would actually do the learning at the edge in real time. So essentially what this means is you do deep learning in a large computer center such as this one, and then this more kind of plausible or neuromorphic learning at the edge. Okay, one way to achieve this, which is actually a method that came out a couple of years ago already, is it's called meta-learning, model-agnostic meta-learning, where the idea is that you train a neural network to learn how to learn, and the way you do this is to learn an initial set of parameters such that it would take very few steps for this neural network to achieve a reasonable performance on a new task. So if you look at this figure here, for instance, as you're learning, you're in this parameter space, you achieve this parameter set here such that it only takes you a few steps to go to these 3 parameter points, which each of them would correspond to a good performance on task 1, task 2, or task 3. The beauty of this approach is that it is model agnostic, and it uses the tools of auto differentiation. So basically model your learning rule in PyTorch, and you differentiate that learning rule in order to optimize this point. So that's the technique called model agnostic meta learning. So I didn't tell you much about neuromorphic hardware itself, but this is really where we decided to take this neuromorphic hardware dynamics and to plug it into model agnostic meta learning. So I'll tell you a few words about what neuromorphic hardware actually is and how we use it. So neuromorphic hardware basically consists of a special type of neural network, usually called a spiking neural network, which replicates the biological dynamics that we know from cortical neurons. So usually what we do is, I'm not going to go so much into detail here, is that we express these biological dynamics into a form of effectively a type of recurrent neural network, such that we can apply the same tools as in deep learning to train them. So we can really define some objective function that depends on the output spikes S. These output spikes are produced by these spiking neurons, which basically also take their inputs as these spiking events. They integrate them on their membrane potential, and they produce themselves the output. So it's a fully kind of event-based neural network. And these are implemented now in a wide variety of different systems out there, some from companies, others from academia. And what we do here is, using the tools of machine learning, especially the theory of machine learning, we derive learning rules, usually based on gradient descent, that can actually be implemented in a local fashion in this hardware. And in fact, this Intel Loihi and some of the chips from this company here have these learning rules built in. So the message here is that we can have this neuromorphic hardware that's essentially efficient, real time, and it includes these plasticity rules, such that we can do learning online on the chip. So it's a fantastic system for this type of real-time, real-world learning. So our first demonstration of this bio-level learning was transfer learning. So you can basically train a network to recognize gestures. You do this offline. You train it using backpropagation through time. Using a model of this neuromorphic chip from Intel called the Intel Loihi. Once we've trained this, we transfer the parameters onto the Intel Loihi, and we use the learning rules built in there to train the neural network to learn, for it to be able to learn new gestures. So in fact, after we've mapped these parameters, we can learn a gesture with reasonable accuracy just after a single shot. And so this was really our first step into this TUFA example I started with. However, this was just a transfer learning approach. Actually, the training method had no idea how the chip itself was learning. And so this is where it actually pays to use this model agnostic meta learning approach, which itself optimizes the learning rule itself, as I mentioned. But now, instead of optimizing an artificial neural network, a deep neural network, we optimize this model of a neuromorphic chip, and then we map these parameters onto the neuromorphic chip. In order for MAML to work, by the way, you need to have a data set of data sets, essentially. And so this is, we've constructed special data sets for this purpose, based on these neuromorphic sensors, which themselves produce these event-based outputs. And here the results were extremely good. I mean, we essentially either match or even sometimes exceed the performance of traditional neural networks. And we exceeded mainly because our data is actually pretty well suited to the spiking neural network, whereas the deep neural network doesn't, it's not really made for classifying sequences. And so the message here is that we can pre-train a set of parameters such that it can achieve this really high accuracy after just a few shot accuracy. Okay, so now I'm just going to wrap up here on why, again, this is, I think, really the approach to go for in neuromorphic hardware. On the one hand, it's simplicity. So the learning rule that you actually have deployed at the edge is the very simple gradient descent. It's not Adam or other optimizers. It's just a pure gradient descent update. So this means that your hardware can actually be extremely simple. It's very efficient in data and memory-wise, because in order to learn quickly, to do few-shot learning, you need to have one big update, which means that you don't need to have that small learning rate, which may also mean you need to have a lot of storage in order to store all these small weight updates. And in fact, we do observe this in our approach. Endurance as well, of course, if you're making few-shot learning, just need one update step, so it's really robust to that. It's very flexible also in the sense that any dynamics can actually be recruited for learning. It doesn't have to be just this like synaptic learning, or you can really use any dynamics in the network. And it's also naturally privacy preserving, because at deployment, when you're learning a new task, all that data can remain local. It doesn't need to go to your computer. It doesn't need to be shared there. And finally, I'll just make this very quick point here. Something that we're working on right now is, of course, in neuromorphic hardware, we're also interested in using nanotechnologies, new memory technologies for storing the weights in computations, in particular these memristors. The problem with memristors is that they are very nonlinear. If you try to update their weights, in fact, the update depends on the current state conductance, and it depends also on the direction in which you make the update. And this does lead to problems. So as if you have some nominal accuracy here, which would be close to 99%, as you increase this nonlinearity, the performance goes down a lot. So actually, in terms of, in this case, this meta learning, you can actually train it in order to compensate for those kinds of updates and nonlinearities, so that learning is actually robust to the nonlinearities in your devices. Okay, so that's all for me right now. So I'd just like to thank the people I've worked with and the people who funded me. Okay.
Thank you so much, Emre, for that talk. And I think it's an interesting perspective on robustness from a meta-learning and a few-shot perspective. We have time for one question. Is there any question from the audience? Maybe just one comment, like, something that I was wondering is, like, as you said, like, when you do this meta-learning, it is extremely data set dependent. So how do you think, like, because you're working with spiking networks, so do you think, and you've got these very interesting results where it exceeds the performance even than baselines. So do you think this is more suitable in a DVS kind of environment or continuous stream environment rather than when, like, the standard static image recognition scenarios? And also, can you give a perspective on how we can, like, because you're looking at more inference right now, but how we can adapt such algorithms for online learning on hardware per se?
Actually, so I'll just quickly answer your second question. So this is actually online learning, right? So we're looking at inference as the task that we're trying to run, but the actual task is a learning task. Okay. When I show, for example, the accuracy here, this is so you start on a new task, which is a variation, which would be a variation of these guys. And then you try to learn that one. And after one shot, you get 99% accuracy. So it is exactly this. It is a learning task. And on your first question, is this better suited for spiking neural networks? I think it's, it's not neither better or worse. It's really, in fact, it is rather difficult to train spiking neural networks with model agnostic meta learning because it involves second order gradients and unrolling in time. And so it's very memory hungry. So we're trying to find methods of actually simplifying this, but there's no main difference between the two. Okay. Not spiking, not spiking. Thank you.
Thank you so much, Emre. This is wonderful. Thank you.
Bye-bye.
Okay. So I think we can move on to our second session. And our second session is on architectures and system. So again, we have 3 speakers in the second session. And our first speaker is Professor Diming Chen from University of Illinois, Urbana-Champaign. Professor Chen is the Abel Bliss Professor of the Granger College of Engineering at UC, and his current research interests include system-level design methodologies, machine learning and acceleration, reconfigurable computing, and hardware security. And he has won several awards, and he's an IEEE fellow. And today he'll be giving a talk on secure and trusted computation on remote FPGA accelerators. So thank you, Professor Chen, for coming and giving this talk. Please go ahead and share your screen.
Okay, thanks a lot, Priya. Let me share my screen. Okay, so you can see my screen, right?
Yes.
Sorry, it's so it's early morning, right? I just had a cup of coffee. Yeah, so I'm sorry, my throat is not doing well. All right, so we all know it's not a secure world, right? So there's a war ongoing in Ukraine, right? So we definitely stand up for Ukraine, and we all know cybersecurity is also a serious threat, right? So even supposed to be secure systems can be under attack, right? So we are all familiar with this. So previously, so my group has worked on cybersecurity for smart grid. We also worked on hardware design to fight against side channel attack, etc. But today, I would like to mainly focus on FPGA accelerators, okay, and specifically FPGA accelerators in the heterogeneous cloud, okay. So FPGAs have been around for about 35 years or so, right? And you probably heard that AMD just acquired the Xilinx, right? So why they are doing that? Because they realize that FPGA is a powerful computing engine, okay? So now, right, so these big companies would have CPUs, GPUs together with FPGAs, right, in the cloud, right? Supposedly FPGA can offer low latency, right, customized computing, right? But one potential difficulty faced by the FPGA world is the programmability for FPGAs, right? And however, people have made significant improvement from this aspect. High-level synthesis is really becoming very popular, you know, in the FPGA world. So actually, FPGA 2022 is ongoing, right? Exactly the same time. Right? So yesterday we had a workshop on open source source-to-source transformation for high-level synthesis. And many people attended that workshop, right? So we are looking into how to further improve the design productivity for FPGA. However, for this talk, we'll focus on security involving FPGA. So where are the vulnerabilities, right? So we always have human errors, right? So hopefully the higher design productivity, right, using high-level language can help us to reduce the human error. But you know, the second main issue is the trusted computing base, right? PCB is too large, right? So that means that the attacking surface is pretty big, okay? And so what are the solutions, right? So here I just listed two of them. There are more, right? So cryptographic approach and even hardware-assisted trusted computation, right? So for example, I will talk about the root of trust established using FPGA chip itself, right? And then because it's a piece of hardware, actually it's relatively harder for the attackers to hack into. Okay. So we are familiar with this term called TE, right? Trusted Execution Environment, right? So on the left side, this is an example provided by Intel SGX, right? So it create enclave, right? And then the trusted functions can only be called from the enclave, right? Even the privileged system code, right? Operating systems, etc., BIOS cannot really get into it. Okay, so then this just provide a tightly protected environment. Okay, but then of course it also incur a lot of overhead in terms of performance, right? So then that's where actually FPGA can also play a role, right? Because it's a customized computing, it can help improve the computation speed and reduce the overhead, right? So overall, we want to provide support for isolation and trustworthiness from the hardware architecture and reduce the size of the PCB, right? And then, so we have a bunch of examples, but none of these actually work for hardware security, okay? So then our goal is to provide the isolation and the privacy guarantee to FPGA accelerators. All right, so here's the threat model, right? So what is trusted? The hardware and its vendor are trusted, right? And the TEE, the enclave framework, right? So for the cloud service provider, it's a semi-trusted, which means that they have all the good intention for security, but they might be compromised, right? Due to various malicious attacks and etc. Okay, and then the rest of the system is untrusted, right? So especially there might be some malicious applications, right? And they cannot be trusted, and the applications are mutually distrustful, right? So this is especially true when we deal with multi-tenancy that try to share FPGA accelerators in the cloud. Okay, so if you look at the current cloud host FPGA system, right? And here this is a high-level representation. So we do have the host side, right? And then the host side can be secured, right? Just using, let's say, Intel SDX, right? It has the enclave, right? It has the secure monitor, etc. Right? So we assume this part is secure, right? However, on the FPGA side, indeed, there's a lack of protection. And for example, many accelerators can share the same memory or share the same bus. If there's a malicious application that can sniff, right, and steal information. And so if attacker hack into the communication, for example, right, and then it may even hijack the computation of the accelerators, and the accelerators are doing a lot of computation, but for the wrong purpose. Okay. So then here is our contribution. We want to provide a secure isolated environment for FPGA accelerators and a remote attestation. That means we can remotely authenticate accelerators and shell, right? So this is important for FPGAs in the cloud. And then we want to establish reconfigurable hardware root of trust, right? So this work is published in a conference in 2021. Okay, so let's look at the strategy for secure FPGA, right? So the first strategy is to extend isolation for security, right? So this we can work with FPGAs naturally, right? Because FPGA support this partial reconfiguration, right? So we just talk about accelerators may, step on each other's toes, right? So we need to make sure each of the accelerators is separated from the other accelerators, right? So then this isolation will control the I/O access, control the memory region, control the data transfer. So each of the computation accelerator has its own, right? So then you can see on the left side, we have the secure monitor to control the software side. And then on the right side, we will create the FPGA secure shell, right? That's the corresponding counterpart to work with the software side to make the whole system secure. Okay, so in terms of the communication, right? So this is quite important. Not only we encrypt the communication, we also make sure each accelerator has its own session key, right? So then, they really cannot understand what's going on, when the communication is taking place. So there's no way for them to tampering each other. Okay. All right, so here is the more detailed block diagram of ACGuard, right? So let me introduce some more details. So here on the host side, we create a FPGA service enclave, right? It's called FSE, right? So this is the contact point for user applications to interact with the FPGA. Okay, and then on the right side, we created this security manager on top of the FPGA shell, right? So FPGA shell, you can treat it as a operating system for the FPGA, right? So it's a bridge to communicate with between the host and the FPGA, right? So for the FPGA shell, that's done on top of the static region, right? And then we design this secure manager that handles the secure communication channels, remote attestation, and the hardware root of trust of FPGA accelerators. And then you can see the security manager will control this ICAP port, right? It's a configuration port to manage partial reconfigurations for the accelerators. And because this shell is secured, right? So I'll talk about more details here later. Because the shell is secured, and then the attacker cannot, for example, hijack this port and then getting control to the accelerators. All right, so sorry. More details on the security manager with hardware root of trust. So here we support the key exchange protocols, right? And then there is a private key for the shell, right? So that then the shell can be authenticated. Okay? And then we also put the public key of this trusted authority, right? So there's a trusted authority. That means the entire environment security need to be rooted by the trusted authority, right? So based on our threat model, okay. And then we also use this TA to generate a device root key, right? So using the FPGA's DNA, right? Because each FPGA is different, right? So we can use, for example, a path, right? Implemented on top of the FPGA, right? Or a random number generator, right? That can be used as the FPGA's DNA and then copied into the secure storage on FPGA. And then this root key will facilitate device lookup table, device lookup, right? Because there are many, many different devices in the cloud and authentication in the remote attestation. And then the shell bitstream can only be operational on the FPGA with the correct device root key. Right? So this is how we establish the root of trust. Okay, and then we, in terms of support for attestation, we will securely send the internal state back to the host enclave, right? And then the attestation report, right, including state from the accelerator, can be completed in the host enclave. And then FPGA shell provide useful modules, right? So because these things can take time, right? We will leverage the FPGA also to make sure they can run faster, right, on top of the accelerator. So we designed a remote attestation protocol, right? So I don't have time to talk about all the details in the paper. But in general, right, steps 2 to 6 establish the mutual trust between FPGA shell and the host service. And then we perform the remote attestation with the TA. And then step 11 onward, load the partial bitstream of the accelerator, right? And then the procedure aborts if authentication fails or result mismatch happens in any of the steps above. Okay, so we provided a proof of concept implementation, right? So then this is implemented on real board, right? So that is that board, right? So it has 2 ARM cores, right? So one of the ARM cores runs as host and secure monitor, okay? And the other CPU core is integrated into the shell and the security manager to control accelerators data flows. And we actually use Hello sensors together with RTL to produce the final design, right? And then here we used a interesting kind of benchmark, right? It's a proof of concept right? Because you can use it to manipulate it and study various aspects related to the security, right? It's a histogram application. And we will compare to a software version secured by Intel STX that's running on a very powerful CPU. Okay, so here are the resource utilization on top of the FPGA, right? So here, this is the overall intensity value distribution for the spectrum. Okay, let's look at some results. So as we can see, we can freely changing the input size, right? So then we can stress the whole system and look at different aspects of the performance. So here we have 4 bars, right? So far unprotected, right? So that's the pure benchmark without any protection. And then accelerator unprotected, right? So the accelerator actually implementing that benchmark, but not protected. Okay, and then we have software secured by the Intel STX, accelerator secured by ArcGuard. Okay, so then we can change in the input size, and then when the input size is very big, and actually we see a big difference. For example, this is a software, right, and unprotected, and this is accelerator unprotected, and we can see accelerator is much faster. But if we compare the same performance, right, for the protected ones, right, you can see the protected one for the software, the Intel STX actually has a huge overhead, and then the accelerator-based protection is much better. Okay, so here this is just showing the same data in a different way, right? So here this purple curve is the speed up of accelerator over the STX software version, right? So then you can see sometimes it can reach 9x speed up. Okay. And we also look at the communication overhead because it's one of the major bottleneck also, right? And we compare with the unsecured baseline, and the ArcGuard can work with different data movement, right? AXI Lite or DMA, right? So then, yeah, so if we enable memory correlation using DMA, right? So in pipeline fashion, then the communication overhead can be very, very small. Okay, however, if AXI bus or something like that can have a very high overhead. Okay, so in conclusion, ArcGuard provides hardware root of trust and secure FPGA shell working collaboratively, and provides a unique hardware enclave framework, supports isolation, remote attestation. And we have a proof of concept that shows that ArcGuard can achieve much smaller performance degradation than the same application running a state-of-the-art Intel STX enclave framework. Okay, and then future work, right? So support for more and larger benchmarks, and work with bigger FPGAs, and support for concurrent multiple accelerators. This can work together with FPGA virtualization. So we have another project working on that, right? And then formal verification of the remote attestation protocol. Okay, thank you.
Thank you so much, Professor Chen, for that talk. We do have time for one question from the audience, if anybody has a question. So maybe I had one question, and which probably relates to some of the future work ideas you have provided here. So I was just wondering, like, this is a very interesting work that kind of accelerates this security aspect. So have you thought of how you can use it for in virtual platform and distributed computing platforms where you have multiple such remote platforms talking to each other? And then do you think that you need to have like local ArcGuard for each platform, or do you think you can have like this kind of a hierarchical global and local ArcGuard configuration? Just wanted to hear your thoughts on how you can apply these in, like, you know, virtual distributed computing platforms.
Yeah, that right. So that's a very good point. So right, so we are working on a virtualization project, right? So by the way, there is a Xilinx Center of Excellence. I should call it AMD Xilinx Center of Excellence at the UIUC. that I'm directing, and there are many different activities there, right? So recently we did complete a virtualization system where it's supposed to go even cross multiple FPGAs, right? So so that means it becomes transparent to the users, multiple applications come and go, right? And then the computation can either be allocated into a single FPGA or cross multiple FPGAs. And then the virtualization itself can provide isolation, right? So then we are thinking about add AppGuard for each FPGA, right? So to secure each FPGA, and then using bottom-up approach, the AppGuards, each AppGuard can coordinate, right? Indeed, it's a hierarchical solution, right? That's more scalable in a cloud computing system. Yeah.
Got it. Thank you. Thank you so much. Okay, so maybe we can move on to our next speaker in this session. Professor Chen, please feel free to stay by, and if there are any questions, please feel free to answer them on the chat. So our next speaker is Professor Onur Mutlu. He is the professor of computer science at ETH Zurich. He's also a faculty member at Carnegie Mellon University, where he has held the Strecker Early Career Professorship. And his research interests include computer architecture, systems, hardware security, and bioinformatics. And today he'll be talking about the story of Rowhammer. So Onur, please go ahead and share your screen.
Okay, thank you, Priya, for the introduction. Let me share my screen. Okay, can you see it?
Yes.
Okay, great. Okay, now I can see it also. I'm going to talk about Rowhammer in this talk, including the fundamentals as well as some recent research. I have a lot of slides. It's a high bandwidth talk, but I'll try to skip a lot of slides also. I'll make these slides available to anybody who wants it. So what is Rowhammer? Basically, it's the fact that you can predictably induce bit flips in commodity DRAM chips today, and many chips are vulnerable. They were vulnerable in 2012, and they're still vulnerable today. What's interesting about this is that this, I believe, is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And as a result, people are writing articles that look like this. Forget software, now hackers are exploiting physics. And clearly, we knew a lot about memory technology scaling for a while. This is one of the summary papers that we wrote about 8 years ago. And especially DRAM has not been scaling very well, dynamic random access memory technology. As we reduce the size of a DRAM cell, its reliability certainly reduces due to issues in the capacitor, access transistor, as well as the sense amplifiers. And we know that you get more errors in DRAM chips, especially based on the large-scale studies that people have done, including us with Facebook in this particular case. As the chip density that's employed in a data center increases, you get higher server failure rates because chips are more vulnerable to reliability issues. And if you're interested, there's a lot of data in the field. But we really wanted to understand these reliability problems by doing small-scale experiments using FPGAs. And that's why we built some infrastructures that look like this. For example, these are FPGA-based memory testing infrastructures. And we open sourced it in 2017. Anybody can use it. People are actually using it in industry as well as academia to do very interesting studies, and we'll be very supportive of that. And you can find it over here. While we were doing a lot of studies with these infrastructures together with Intel, we found out that basically you can predictably induce errors in most DRAM memory chips. And that's the DRAM Rowhammer phenomenon that I mentioned about. So what happens exactly in Rowhammer? You have multiple rows in DRAM. And if you repeatedly access one row, meaning apply high voltage to that row and then apply low voltage, this is called activate precharge in DRAM, activate precharge, activate precharge, activate precharge, essentially access one row. It turns out physically adjacent rows get bit flips. We call this a hammer row, we call this a victim row, and clearly this should not happen, right? You, based on memory isolation principles, whenever you read from memory, you should not modify any data, including your own data, but now you're modifying some other data that may potentially belong to someone else. And this is a widespread industry problem. Basically, this did not occur in chips that were manufactured before 2010, and the first appearance is in 2010. And all chips that we tested that were manufactured between 2012 and 2013 were actually vulnerable to this effect. So this is a scaling problem, technology scaling problem, because at some point cells became too small and too close to each other. As a result, the electromagnetic interference is affecting cells that are close to each other. And what is worse about this is now a simple program can induce many errors. You can write an assembly program like this. This is what we released when we actually wrote our paper. And what this program does is basically it accesses rows X and Y in a single DRAM bank. And if the chip is vulnerable, hopefully you'll get bit flips. This is not the worst program you can write. You can actually write much worse programs, as later folks showed. But our proof of concept at the time showed that this is a real reliability and security issue. And we demonstrate this on Intel and AMD systems. And essentially, if you can write such a program, you can also take over a system because you're breaking memory isolation right now. And Google Project Zero folks were the first to show that you can do this on a real system, taking over x86 64 Linux. I'm not going to go through the slide, but this is essentially copy and pasted from their blog post, Google Project Zero's blog post. What they did was they were able to replicate the Rowhammer problem and induce bit flips and page table entries. And as a result, as a user level process, they could gain write access to the page table of that process. And once you gain write access to your own page table, you can actually circumvent any type of protection on the system. And as a result, people actually are were making jokes like this. These are famous hackers, actually. It's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. I kind of like this analogy. There are a lot of actually interesting attacks that were developed due to this Rowhammer, software-inducible bit flips. I'm not going to go into the details since we don't have time, but you can see a lot of very interesting papers published at top security venues, taking over different kinds of systems, even through remote direct memory access, or leaking data, breaking confidentiality, for example. Even if you cannot actually take over the system, you may actually break confidentiality and actually leak data from the system. And more recently, we've been seeing some papers that show that neural networks, if you actually target these bit flips through Rowhammer, an otherwise perfectly accurate or reasonably accurate neural network may lose its accuracy completely because you get these bit flips. And there may be other interesting attacks, for example. So if you're interested in a lot of this, we cover in this survey paper a lot of issues related to Rowhammer across the stack. But keep in mind that this is from 2019. Now, let me quickly mention, understanding Rowhammer is important actually to build real systems. And that's what we did in our first Rowhammer analysis paper. That's what we have been doing by building new infrastructures. And initially, we tested 129 modules. You will see more recent results soon. And again, I'm not going to bore you with the analysis, but there's a lot of interesting analysis about the Rowhammer phenomenon. And you can find that in this paper. And more recently, we've shown that Rowhammer is getting much worse. And I'm going to talk about this briefly later in the talk. And more recently, even more recently, we showed that Rowhammer is actually getting even worse than we thought because it has many, many dimensions. I will mention this also in a little bit. But before I mention those recent studies, let me talk about Rowhammer solutions a little bit. What kind of solutions do we want? First of all, clearly, some chips in the field are vulnerable. So we need to immediately protect them. And there are limited possibilities we have. Increasing the refresh rate is one. Longer term solutions need to be more fundamental, I believe. And we should come up with a wider range of protection mechanisms. And in our original paper, we propose multiple solutions. And I will describe one solution that I still believe is interesting, but it needs to be augmented today. So these are some solutions that I don't believe work extremely well because they come up with high cost, high power, high performance, etc., and complexity. Especially making better DRAM chips is difficult because isolating cells have been proven difficult. And refreshing frequently, although that's been employed, is not a great solution because it clearly increased the energy consumption and performance overhead. I'm not going to talk about the details. You can find that in our survey paper. So what the industry employed in existing systems is increasing the refresh rate because that's the simplest thing to do. And that's the configurability you have in your memory controllers today. That's a bit unfortunate because our memory controllers don't allow us to patch things or make things, essentially patch things so that you can prevent issues like this by executing programs or executing code potentially. So our solution, our proposed solution require changes to the memory controller or the DRAM chip. And the idea is very simple, probabilistically activate adjacent rows. After you close a row, with very little probability, activate adjacent rows, neighbors. And if you do that, you essentially refresh the data before, and you actually get rid of the hammering effect by refreshing the data quickly before the charge gets lost. And as a result, you get significant reliability guarantees, which you can adjust with a user configurable parameter. And this is a nice solution. It requires to be reinvestigated even more, in my opinion, to actually be much more scalable going into the future. We'll talk about that in a little bit. But you can implement solutions in the DRAM chip or in the memory controller. This kind of solution can be implemented in both places. It was actually done by Intel in the memory controller with some caveats. Today, versions of it are implemented in the DRAM chip, but we will talk about the caveats of that also because they're not necessarily implemented in a secure manner. And this is an example of the solution that was that was done by Intel at the BIOS level. And again, for details, you can read the papers that I mentioned, including this one. So takeaway, I think if you really want to solve this sort of scaling problems, we need intelligent controllers to enable better scaling, security, safety, and reliability, because Rowhammer is in the end such a problem. And I think we know how to build intelligent controllers, except for other memory technologies. This is NAND flash, for example, and we know exactly how to build these memory controllers for slower memory technologies. Now we need to figure out how to do that with much faster memory technologies like DRAM. So if you're interested in Rowhammer, there's a lot more analysis I mentioned. I'll quickly now go into what has happened recently in 2020 and 2022, because a lot of interesting things happened in Rowhammer. First of all, as I said, we revisited Rowhammer. We wanted to understand its scaling, and we did a large-scale testing study of more than 1,500 DRAM chips, and we found that essentially that newer DRAM chips are much more vulnerable to Rowhammer. You get more bit flips that happen earlier. In fact, there are some chips whose weakest cells fail after only 4,800 double-sided hammers. This is a very low number. And unfortunately, existing mitigation mechanisms are not affected at future technology nodes. They may work at higher technology nodes, but as the technology scales, they become very ineffective, meaning either they don't work or they have very high overhead. So they're not scalable. So that's just one example, basically. Newer chips are a lot more vulnerable, as you can see, compared to the older chips in this study. And bit flip rates increase with technology node generation. This is another example. Newer chips from each DRAM manufacturer are found to be more vulnerable to Rowhammer. I'm going through this relatively quickly because we don't have a lot of time, but you can find a lot of details on the papers. And you can also find a lot of lectures. Let me talk about the trespass issue. Here, we wanted to understand basically whether industry adopted solutions work. Industry basically said, DRAM industry basically said, we solved the problem, trust us. And of course, as a researchers, we should not really take this as a given. So what we did was we basically tested that. And we showed that TRR protected, target row refresh protected DRAM chips are vulnerable to Rowhammer in the field. Mitigations that are advertised as secure are not secure. And this introduced a many-sided Rowhammer attack. By hammering many rows to bypass TRR mitigations, industry internal mitigations in DRAM, you can overflow proprietary TRR tables that detect aggressor rows, essentially. And we did that by partially reverse engineering these mitigation mechanisms. And we also provide an automatic tool that can effectively create many-sided Rowhammer attacks that anybody can use. And in fact, people have been using that. So many-sided attacks are basically hammering more than 2 rows. That's the idea. And you basically get bit flips in protected chips, advertised as completely secure against Rowhammer, after you hammer more than, let's say, 5 rows, 7 rows, 10 rows. And in some cases, 19 rows, actually, yes, 19 rows. And this actually, you can actually take over mobile phones that are vulnerable this way. And attacks are actually really fast, as you can see over here, and you can read the details in the paper. So basically, this was a proof of concept that shows that real chips that are actually implementing protections are vulnerable, and mobile phones are vulnerable. And these results are were scratching the surface because our tool was not exhaustive, and there was a lot of room for uncovering more vulnerable chips. Clearly, Rowhammer is still an open problem, and security by obscurity is likely not a good solution. To solve the problem, we really need better security mechanisms implemented in industry. Okay, so we also wanted to ask the question, how do you guarantee that a chip is Rowhammer free? Unfortunately, there's no good answer to this. I don't think that you can guarantee that at this point. We don't have a good methodology to do that. I'm not going to talk about this, but you can find information in this paper. Later, we said that, oh, can we uncover these TRR mechanisms that were adopted by industry completely? And we almost succeeded that. I'm not going to say completely. We really succeeded almost completely. And the idea is to use this new methodology that leverages data retention failures to uncover the inner workings of TRR and study security. We basically developed this methodology that enables us to craft new Rowhammer access patterns. And as a result, we can actually circumvent all modules we tested. We can see a lot of vulnerability in real chips, and ECC is completely ineffective. Okay, so this can hopefully facilitate, this work can hopefully facilitate more secure Rowhammer protection mechanisms. The key idea is really used to data retention failures as a side channel to detect when a row is refreshed internally by the DRAM chip. So DRAM chip is doing internal refreshes to prevent Rowhammer, and you can actually find out information about that because there's a side channel created. And we did real studies from 45 chips over here. You can find a lot more information in this paper. And I'm going to skip these because this has basically overall more information. And there's a lot more information than I described also in the paper. New Rowhammer characteristics are also interesting to study. And this is a recent study from Micro 2021 that we did. We wanted to understand 3 fundamental properties and their effect on Rowhammer: temperature, how long the aggressor row is active, and physical location of the DRAM cell that you're targeting. What is the variation of physical location? And we basically developed an understanding, again, using experimental studies. This is our latest infrastructure, actually, with DDR3 as well as DDR4 based. And we did studies on 4 different manufacturers in this particular case. And basically, we found out that a Rowhammer bit flip is more likely to occur in a bounded range of temperature, which depends on the chip. if the aggressor was active for a longer time, and in certain physical regions of the DRAM module under attack. So if you target certain physical regions, you can actually be more successful. You can use this to create more effective attacks, as well as more effective defenses. And that's what we did. For example, by understanding the aggressor of active time, a better attack can reduce the minimum activation count to induce a bit flip by 36% and can bypass defenses, sorry about that, that do not account for this reduction. And also you can improve the defenses by making them more efficient because you don't have to protect the entire DRAM chip at the same level of aggressiveness. And there are more analyses in the paper, but I do not have time to talk about that. Let me talk about new Rowhammer solutions because this is a very important direction. There's a paper in ASPLOS 2022 that's coming also on this. There are 4 major mitigation approaches: increasing the refresh rate, physical isolation, reactive refresh, and proactive throttling. And these approaches have many key challenges, but 2 important key challenges are: how do you make things scale with worsening Rowhammer vulnerability into the future? And how do you become more compatible with commodity DRAM chips? Ideally, you don't change anything in the DRAM chip from a memory controller perspective. And our goal was to actually achieve both of them. And the key idea in this work is to selectively throttle memory accesses that may cause Rowhammer bit flips. I will not go through the details of the approach to implement the memory control. It's an intelligent memory controller approach. I will let you read the paper if you're interested. But basically, this approach is competitive with state-of-the-art mechanisms when there's no attack and superior performance energy. And can, with very high probability, detect a Rowhammer attack. And you can kick it out from your system or do more analysis if you will. And enables better hardware area scaling with Rowhammer vulnerability while having a security proof. And we study 14 mechanisms representing 4 mitigation approaches in this work. And you can see that analysis. I believe going forward, we need to have more rigorous analyses of Rowhammer defenses into the future. So basically, the takeaway, in my opinion, is that main memory needs intelligent controllers for security, safety, reliability, and scaling. That controller may be implemented inside the memory chip or outside the memory chip, but I think we need to do more. So there's a lot more work that I did not cover. You can find more information about these papers. This is from 2021. 2022, actually, this is the paper I mentioned at ASPLOS 2022 that's coming up. I believe there's more to come. I'm going to skip this part about future challenges. There are other technologies that are also challenging. Sorry about this. But I think, again, intelligent memory controllers can avoid the failures and enable better scale. So let me give you some final thoughts. This is a very paper that I really like, actually. It's from IEEE Security and Privacy from 2003. It was written ahead of its time, maybe. These folks actually used memory errors to attack a virtual machine, take over a virtual machine, basically, bit flips. The way they induced bit flips is by heating the memory on this machine. This is before Rowhammer. I think this paper needs to be given more credit, frankly. But after Rowhammer, those bit flips, you don't need physical access to the machine. A simple memory error can be induced by software because of Rowhammer. So I believe Rowhammer enabled a renewed interest in hardware security attack research. Real memory chips are really vulnerable through software, and hardware reliability and security connection is now mainstream discourse. There are many new Rowhammer attacks. I believe they will keep coming. Many new Rowhammer solutions. I believe they should keep coming so that we can actually be safe and secure. And basically, I think Rowhammer is proof that general purpose hardware is fallible. I think we really need to examine other general purpose hardware as well. And this is happening, I think, at a scale. Google and Facebook both published papers on silent data corruption. More recently, in 2021, actually, there's a HotOS paper by Google on chips that do not work, for example. Okay, I'm going to skip this one and conclude, basically. So takeaway, I think, is memory reliability is reducing. Reliability issues open up security vulnerabilities, also safety vulnerabilities. These are very hard to defend against. Rowhammer is a prime example. And as I said, this is the first example that I know of a simple hardware failure mechanism that can create a widespread system security vulnerability. And I believe its implications on system security research and defenses are tremendous and exciting. The bad news is Rowhammer is clearly getting worse. And good news is we have a lot more to do in all parts of the industry and academia. We are fully aware that hardware is easily fallible. We're developing both attacks and solutions, and hopefully principled models, methodologies, and solutions to fix the problem. And again, if you really want more, the survey is a 2-year old survey that talks about a lot of these issues that I mentioned, and you can find more information online. I will thank people for funding us and definitely thank my research group for actually being part of this research over the course of 8 years. And these are them. Thank you very much. I'm happy to have any questions.
Thank you so much, Professor Mutlu. That was really a very informative and a packed talk. So we do have some time for questions. So if there is any question from the audience, please feel free to unmute yourself and pose a question. Maybe like I can start off like, so I was just wondering, and you I think pointed up briefly around it that, technology scaling is not helping with Rowhammer attacks. And maybe you showed a perspective of DRAM, but as new technology is coming in terms of embedded memories. So what do you think is like, do we always come up with this, like, every time we come up with a solution and then we attack it? Or is there a way to universally approach some kind of a robust from a technology side or from an architectural system? So what is your perspective on how to develop a more robust end-to-end scheme for such kind of hardware security vulnerability?
That's a great question. Those are some of the slides that I skipped in terms of future memory security reliable challenges. Clearly, DRAM is a very important technology, and any error exposed in DRAM is directly exposed to the programming language data structures, right? That's why Rowhammer is very, very interesting. But yes, I agree. There are other memory technologies that also have similar problems. Some papers have demonstrated that, usually in simulation, sometimes in real chips also. I believe if we understand the solution really well, then we can develop fundamental techniques across memory technologies. Even though different memory technologies have some differences, I think moving data, refreshing rows, we can develop general solution classes. But I think it really comes down to understanding the solution, understanding the problem really well with using these studies and developing these architectural methods that can solve the problem in different design points, because different memories are also in different points in their development. They may not need as much protection, but you may have some configurable protection mechanisms like refreshing, probabilistic adjacent row activation is one example, block hammer is another example, that you can adapt to different memory technologies. So I believe, short answer to your question is yes, I think we can find fundamental solutions, but we need to somehow configure them to different memory technologies to be really efficient in a given setting.
Got it. Thank you so much. Are there any other questions? Okay, if not, thank you so much, Professor Mutlu. That was a wonderful talk. And please stay back. If there are any questions, please answer them on the chat. And definitely all of the slides as well as the talk will be available for later viewing as well.
Okay, thank you very much.
Thank you. So moving on, our next speaker is Professor Professor Vijay Krishnan Narayanan. Professor Narayanan is the Robert Noll Chair, Professor of Computer Science and Engineering at the Pennsylvania State University. His research effort is supported by DARPA, SRC, JUMP, CBRIC, as well as CRISP centers, and he's a fellow of the IEEE, ACM, and NAI, National Academy of Inventors, and he has won several awards and has done some tremendous work. And today he'll be shedding light on one of his recent work on distributed and multimodal information for robustness.
Good day, everyone. It's always a hard task to follow Onur with a high bandwidth talk, so I'm probably going to do the low bandwidth talk on trying to filter some of the information. So the whole notion here is to basically get to distributed and multimodal information for enhancing the certainty of your decisions while minimizing the content that you need from all these sources. So if you look at many of these multimodal systems, and specifically multi-sensor systems that we have been working with, you have a diverse set of edge sensors, and the information from these edge sensors need to be fused together to get a more global perspective. And the challenge is many of these edge devices are computationally limited, so they may not necessarily be able to infer everything locally. Some of these sensors, just to their nature, are susceptible to failures, noise, environmental conditions, and even worse, the transmission links between these edge sensors, or even the sensing mechanism of these sensors, can essentially be hijacked into by a malicious attacker to try and destabilize the system's overall performance in such collective systems. So in our goal started with trying to make this inference actually more energy efficient. So one of the challenges is for a robust system is to be able to operate within the constraints of the energy efficient system. So questions that we wanted to fundamentally answer: among views, which are the most important? How many such views do you need? And could you leverage things like view correlations for better accuracy? And in the context of this workshop, for safety, can if I see Vijay from one angle and another angle, do they really correlate to Vijay, or are they two different people? And one view is really someone else. So this, we have also been looking at this from application context, just to give you a notion of things that we do. Here we basically have 3 cameras looking at pollinators in a farm. And it also has other sensors like weather sensors and temperature sensors that you can correlate with. And I'll come back to how you can coordinate the information from these sensors to make robust decisions later on. But now let me look at some of the theoretical underpinnings of what we are trying to do. So here you're essentially seeing an object from just 2 different views, a top view and a front right view, among different views that you can see the same object. So the whole notion is each and every sensor could basically process that particular viewpoint and basically say with certainty, oh, this is a bus. Another one could probably say the same view and say, I'm saying this is a ladder, right? So then the notion is, which decision making should we essentially give priority, because each view has a discriminative visual information, and we need to make sure that information is the most critical with regard to classifying that particular class instance. So how do we figure out what information is important? And one of the things that we adopt here is we leverage many of these classification engines are deep neural networks, where you could essentially use the low entropy as a proxy for a high likelihood whatever you're observing belongs to the trained data set. And that really is a function of how you train these neural networks. So we are going to use the quality of information against a trained network to be inversely proportional to the entropy. And this lands up enabling this distributed camera system that we are building, which aggregates closely geolocated cameras into a specific context group. And these essentially are associated with the same supervision of trained data. And then what we'll end up doing is, among these different context groups, we provide a node importance based on the entropy extracted from this context group. And we then aggregate the information coming in from each one of these context groups based on the likelihood estimated from their different viewpoints, using that as a proxy to give it a certain weightage. So if you, for example, if you can really think about this as news coming from BBC, CNN, Fox News, how would you weigh these things with relevance to the entropy? So here is a data point that we show. So here I basically have 4 viewpoints for 4 subclasses of objects that we were looking at. And the percentages that you see here are the statistics of which views had the lowest entropy among all the views in the entire training set. And one thing that's obvious in this data set is if you had a view 1 image being shown, a model trained on the view 1s had the lowest entropy or the best model match in most cases. However, note that the entropy is not a metric for confidence. It's just an uncertainty of a probability distribution. So there are cases where the entropy was the lowest for a view 1 in view 2 or view 4. So what we'll end up doing is we use this metric which has to do with the entropy to normalize the weightage for each of these views that we are seeing. We use this in two different ways. If we take likelihood, which is kind of inversely related to the entropy, if it is less than a certain threshold, we basically filter that information. Hey, this is too noisy compared to the model that we are expecting, so I'm going to throw this away. So it's not even going to corrupt my decision making. The other part that we'll end up doing is we use this likelihood as a metric for weighing in this input among a bunch of different inputs contributing to the decision. So this ends up helping us to throw away a lot of information. So we were able to reduce the communication and corresponding energy by 3x. And I'll show you later on, this mechanism also helps us to recover against targeted errors or failures in this particular system. So our system basically has two different configuration, a 12-view camera and a 80-view camera system. And in this particular scenario, the max rows that you are essentially seeing are the standard ones where you need to aggregate all the 12 views or all the 80 views. Average is basically and basically gets the best out of all those three, doing max pooling. Average pooling is basically giving equal voice to everyone. The weighted average is our approach, which throws away some of these things and provides a weighted mechanism based on its estimated importance. And one thing that we quickly notice is that the weighted average actually ends up doing better than getting all the information. And the reason being is if you cluster a bunch of different sources, it's going to be worse than the most important sources to inform your decision. And the good thing is you're also not necessarily expending or incurring the cost of everything. So that results in improvements in weighted average. So now let's look at what happens when you induce noise and errors in these type of systems. So one key observation is our approach. So in the graph shown here, because of our weighted approach, fewer nodes actually contribute to the higher fraction of accuracy compared to a standard approach where you're basically aggregating over more nodes. So in the standard approach, using just a average mechanism, you would have had 9 nodes in our 12 node system contributing to a 76% accuracy, while just 3 nodes would have contributed to that 76% accuracy in our mechanism. So we define two terms, non-representative node or representative node. So if the failures had happened in one of the 6 nodes that were not the top 3 nodes, our mechanism is solidly doing better. So consequently, if the fraction of noisy nodes are small, much smaller than the nodes that we are basically leveraging the most accurate versions, our robustness is high. However, when representative nodes contributing to the decision start failing, it has a much worse view than the standard one. So there were 2 experiments that we ended up doing and mitigation mechanisms. If you do not know which nodes are likely to fail, then what you could do is you could essentially sacrifice your energy savings by essentially distributing the responsibility to more nodes. And this gains back about 14% of your accuracy. If you know based on deployment or anticipated failure mechanisms, you also have a mechanism to selectively veto certain nodes. For example, if you know a camera or a weather station is in a potentially exposed environment and is likely to fail, you can basically disengage it in this particular notion. So we can again gain back accuracy in these two schemes. So our mechanism is basically a knob between anticipated errors, failures, attacks, and the energy costs of these things. We have been doing things to reason even more. So if you really look at a bunch of different things, if you land up seeing a fork, spoon, knife, and a ball, you probably know, oh, the ball doesn't make sense because it really doesn't go together with other things. But you are thinking as a human, how would we land up doing this same notion in an automated system to verify? So we're really looking at a notion of object relationships and semantic relationships in this particular notion. So one technique that we have been using from the semantic perspective is to leverage WordNet, which is basically relationships of different words that are spoken. And in this particular case, so when you have an object, you basically look at the boy, the dog, the ball, the car, and you're basically creating the visual scene graph in this particular case that is extracted from the video and passed through your networks. But you also compare this with a WordNet, which is basically semantically organized. So if the ball was basically misclassified either due to an attack or through a noise as apple, then the likelihood of dog eating an apple, it's unlikely. So you would basically flag that as an error and then be able to invoke a different model which has been trained with a different distribution to be able to circumvent any of these type of attacks. And that's really what we do. So we do a low power inference, get the model context, and if the model context doesn't really correlate with a semantic context, we refer it to an additional inference to try and figure out some of these anomalies or attacks. And the good thing about these type of mechanisms, while I showed you the WordNet for semantics and a visual image, you could basically use text, you could use audio, you could use other signals, you could use multiple sources to be able to do these sorts of validations and try and do these type of correlations. And a context in which we have been applying these type of multimodal information to deal with. This is embedded system with cameras, and you can see a solar panel powering all the equipment. This is actually at the Penn State Arboretum in summers. We took it down in the winter, of course. So what it ends up doing is it basically gives you information of what type of insects were found, what is the UV that day, is it a rainy day, is it a hot day? And then you can start using correlations. Hey, it was a very rainy day and I don't see insects, makes sense. If I basically see a lot of insects on a rainy day, it means something wrong. Or if it basically says the UV index was very high, but it was a rainy day, something is faulty with the sensors. So these are type of correlations that you'll end up doing. And again, as I showed you in the very first picture, we had multiple cameras. So each of these cameras can basically say, oh, this is just appears to be a shadow. It's happening only when the sun's angle was at a different degree. It's not two insects, but just a single insect, right? So you can make those type of correlations with these type of multimodal aspects. This is a work in progress, and one of the things that we are observing, what turned out to be something that we were trying to do for integrity analysis and ensuring the analysis is good, is now turning out to be an opportunity. So now we are basically using some of this environmental data and sensor data to be able to refine IDing of some of these insects. And there are so many insects, they are tiny, they are small, the differences are distinct. So this is something that we continue to work. And this day and age, these type of validations are really critical, because your sources could be faulty. You're getting information from many sources. Some are trustworthy, some are not. And in fact, a bunch of things may even agree to be in a coordinated fashion to give you false information. So that's really what I intended to share with you. Look forward to any questions that you may have. Thank you.
Thank you so much, Professor Narayanan, for that talk. We do have time for some questions. So anybody in the audience, if they have any questions, please feel free to unmute yourselves and pose a question. Maybe I can get started with, like, so this is very interesting that you're bringing in context awareness to kind of help these different agents, or like, different models to understand when something is missing or one of them is being attacked. So I was just wondering, like, do you bring in context awareness as a part of the learning process, or is it an artifact of the way in which you're doing this multimodal distributed learning? So that was something maybe you can shed some light on.
So as far as doing context aware learning, I think folks like Emre or Gert in the audience may be better equipped to answer that particular question. However, what we are landing up doing is we are almost really looking at things like a graph matching, or we are looking at a graph network. So we are basically creating different types of graph relationships from different modalities and different sources. So for example, the scene graph is a graph that's extracted from the visual information. A word net is basically a semantic graph that is constructed from word usage, right? So what we suppose is these are both information knowledge representation structures. And then what we really see is, are we seeing correspondences in both these knowledge representation features? And if there is not a correspondence between these knowledge representation features, we use similar to arbitration or additional reference to try and sort this out. And one thing that is really important to note, while in the visual analytics, I may actually land up seeing Vijay next to a tiger, right? And then it basically, in the word net, it basically says humans are probably not close to a wild animal in their house. It may still be true that Vijay was in some wildlife sanctuary feeding a tiger, right? So just because the knowledge graphs don't match doesn't mean the information is true, but it probably needs to then go and get a geolocator for that image, or you could basically go back into a history of stored database to see, does Vijay like wildlife, right? Or you could go and look at what are other instances in which tigers are being present with animals, right? That is a lot more exhaustive work. But as a first round, you can basically label this as like a fact checker would do, unlikely. But then when you dig deeper, I might have been false in my flagging that it is false or unlikely, it is actually true, but that's going to take later, right? So that's the kind of work that we are doing. Any work that basically lands up helping bring context in learning, that is good. But the problem is applying context while learning is very challenging, just as I mentioned to you, because context can be very different based on what type of query, what type of things. So there is nothing like truth in many of these things. It is in the beholder's eye, and that's the challenge that we find with misinformation and other aspects.
That sounds good. So I have two raised hands here, Professor Zhu and Professor Kornbergs, both. So maybe Professor Zhu, you can go ahead first.
Thank you. Thanks, Vijay, for the great talk. I have a quick question. So I just wonder, across different views, have you considered, for instance, some of the impact in terms of timing or temporal sort of relation between them? How do you synchronize different views? And can we leverage, for instance, if certain view seem to be more accurate, we may sense more often, right? Questions along those lines.
Yes, so one of the challenges, so there are two setups, right? So in the theoretical setup, many of these aspects are reasonably easy, right? So I can basically look at view importance, I can basically look at attacks and other stuff. What we are really learning, the timing synchronization aspects that you are mentioning. This is the rig that we have with 3 cameras. They are in close proximity, but still trying to infer, especially when we have a bunch of small insects coming in, right? So when I need to count the number of insects, a time synchronization error across these cameras may still pose a lot of challenge to me. And then again, as I mentioned to you, this is actually right now our setup is basically a translucent view to the insects. It doesn't have additional weather protection, other stuff, or other reasons. So you basically get things like raindrops or shadow or dirt in one view, but not in the other view, right? And that basically creates inconsistencies across these views. So having a metric like time to say when this happens, when this doesn't happen, or the continuity of that feature, right? For example, if it's a raindrop or a dirt, it prolongs for a certain time. And then we can basically dynamically change the way. It's not just based on what is viewed, but also based on these environmental conditions. And these are things that we continue to learn. Yes, synchronization is important. And in fact, what we are finding is synchronization of this information to like weather data. And we have been trying to use the local weather station. When I say local weather station, this sensors that we place close enough to weather stations that is there provided by the city. And we are trying to see whether there is this time synchronization errors even there.
Thank you.
Thanks.
There was another raised hand by Gert, so please go ahead.
Vijay, a great talk as always. So you, just a quick question here. So you use entropy as a means for improving, I guess, the resilience, the quality of your I guess the classifications or the computation. Now, so entropy is also intrinsically linked to energy. Is there a way we can that you can use that entropy framework to also minimize the energy or of course, this may go against the maximum entropy principle, but so is there anything that you can also leverage towards lower energy computing as well?
That is something that we need to think, right? So right now, the entropy that I'm using is still a localized viewpoint. So the viewpoint that you're taking, somehow I need to take the entropy of the collective system to be able to do that. I'm not sure whether the way that we fuse the local entropies will lend itself to the energy optimization that you mentioned, but that's something that we need to explore, and maybe I'll poke your brain later offline.
Thanks, Vijay.
Thank you so much, Vijay, for that wonderful talk. And I think that concludes our session 2. So I'll now ask my colleague Yuhao to take over for session 3 and 4.
All right, thanks, Priya. And I guess we're going to jump right into session 3. And in session 3, we're going to switch gear a little bit and talk a little bit about circuits and devices. And our first speaker in session 3 is Professor Gert Kallenberg. Professor Gert Kallenberg is a professor of bioengineering at UC San Diego, where he co-directs the Institute for Neural Computation. And previously, he was professor at Johns Hopkins, and he has won many awards, including the Presidential Early Career Award for Scientists and Engineers, otherwise known as PCASE. And today, he is going to tell us about efficiency and robustness in large-scale neuromorphic computing. Looking forward to it.
Thank you so much. So this talk here will touch on the a linkage between efficiency and robustness applied onto neuromorphic computing. And so let me start by phrasing this in the context of this revolution that we've had recently in cognitive computing. And it took us by almost surprise. At least I was very surprised too. I didn't think that the game of computer Go would have been solved because by computers anytime soon in our lifetimes, but apparently it happened. And so Google DeepMind did it. Now, to be fair, so sure, the world champion here was defeated by the machine, almost this apocalyptic kind of event that happened. But to be fair, if you look at what was under the hood, sure enough, yes, the machine won here, but at a formidable cost. If you look here, so it's about the, if you just in the energy cost, right? If you consider, just generally speaking, that the human here consumes about 100 watts of metabolic power, assuming the whole body was involved here, versus the 100 kilowatts of power that was taken by Google's even optimized the hardware that included all this TPUs, this TensorFlow processing units, right? So still, it was about 1,000 times more power involved in that feat here of defeating the world champion. And so this makes us think. So even though if you look also under the hood, there's actually neuroscience taking place. In fact, the founders of DeepMind actually are neuroscientists, right? So there's definitely some neuroscience iteration that can be taken here. But so there's another aspect of all this. So even though neuroscience has been involved in making systems really effective in computing, there's some efficiency that's lagging behind. Right, sure enough. So, and you can keep pushing deep learning's effectiveness just by throwing more deep learning, this more massive resources of it. And sure enough, yeah, you can get down to really just low error levels, but at a formidable cost. If you consider what it takes actually to reach those lower and improved levels of error. And so there's almost an exponential cost involved in making this incremental improvements. And this just shows, there's a very nice article in IEEE Spectrum that highlights, right? So now to get this further advances in the effectiveness of deep learning, you almost need to consume resources that are massive, right? In terms of even the entire power of a city, or because the entire Boulder, Colorado, because power is the dam there. So things are not very scalable in that regard. So it's important to consider what is going on here. So let's step back here and look at some of the fundamental limits of what is involved there in terms of the costs, the energy cost of computation. And so on one end of the spectrum, we have traditional computing, right, such as central processing units, and so with some typical DRAM memory that is around it, right? And so you have all this work being done because with cache, gives the memory to then interface this slow memory with fast compute, right? And this is the main bottleneck. In contrast, so we have fundamental limits of efficiency given by the Landauer's limit, which are now orders and orders of magnitude, I guess, more efficient, right? And that's really a thermodynamic limit of energy in computation. So in between, so the human brain lies somewhere in between. So if you take the efficiency, so neurons firing about 10 to right, so about right, you have about 10 or 15 synapses, and they fire about at 10 hertz rate. Neurons fire about 10 hertz rate, so together you have 10 to the 16 synaptic operations per second at about 10 watts of metabolic power. So that amounts to about a femtojoule per synaptic operation, which is somewhere between the extremes of the 70 picojoule per bit of traditional computing, and then the KT, right, the Boltzmann constant times temperature per bit that you have. So on the log scale, it's a lot better, but still not quite there. And so now just comparing the advances that have been made in traditional computing. So you can definitely bring memory closer to compute by, say, this high bandwidth memory operations, right? This really that have gotten some advances, but not great advances. So still maybe factor 10 or 100 or so in efficiency, so it doesn't quite get there. And so computing memory approaches that really bring the memory very close to the processor, or actually reversely bring the compute close to the memories, right, have been then more effective in getting us closer to this greater efficiencies. And so what I'd like to get to today is that you can even take this at an extreme, and it can actually really gain, even do better than human brain level of efficiency if you do things carefully and really think of energy in a very fundamental way. And so that gets it into neuromorphic engineering, which is a discipline that endeavors to model what the computation in brain, not only its function, but also in transforming some of the fundamental physical principles, right, underlying physics of computation, directly morphing them into equivalent circuits and organization in silicon integrated circuits. And so this way, those systems inherit not only the functional attributes, but also then the efficiency and the resilience of natural neural systems in silicon systems. And so even though John von Neumann is often quoted as the antidote of much of the, or right, the opposite of neuromorphic / neural engineering, I would actually say that he was one of the very first ones, one of the very first neuromorphic engineers, right, who in his last opus, The Computer in the Brain, he really compared and contrasted the digital compute type of architectures with some of the massive parallelism structures that you have in the brain, and he was advocating for actually getting closer towards it. He was never able to get to it, unfortunately he died, but so others have taken over. So Richard Feynman, whom we all know for, there's lots of room at the bottom, starting basically the revolution in nanoscience and nanotechnology, along with Carver Mead, who also has been very well known for his contributions to systems, visualized systems, right, very large scale integrated systems, from a really, because a system perspective that could really, and in fact, he also coined the term Moore's law. He was a good friend of Gordon Moore, and he saw scaling trends in technology that would underlie these massive advances in information technology. So those have really made their marks on information technology. But also equally importantly, they have thought about this neuromorphic principles in terms of analysis by synthesis. So one of the last things that Richard Rowhammer actually told us, I guess this was the Blackboard just before he died, what I cannot create, I do not understand. So making the case that in order to understand how the brain works, you need to really build it from the ground up. And Carver Mead really took this to an extreme and was starting this field of neuromorphic engineering that takes a look at multiple scales of organization in the brain, and how at each level of scale, this can be mapped, right, owing through physical isomorphisms into equivalents in integrated circuit technologies, all the way from the lowest level of ion channels, which correspond to, say, MOSFET channels, all the way to higher levels of organization. And so in this way, this becomes a complementary endeavor where neuroscientists do analysis, right, because, and engineers do synthesis from the ground up. And so this bottom-up, top-down approaches can be combined efficiently for making progress in both neuromorphic engineering as well as computational systems and neuroscience. And so it's important to think of this at the fundamental device level. So here, even a transistor has direct analogs to, so the channel of an MOS transistor has direct physical analogs to a biological ion channel through membrane. If you consider some of the thermodynamics, right, of say, so as electrons have to move through channel and observe this energy barrier, gives us Boltzmann physics. You also have these barriers of this folding of this ion channel, this proteins, right, that govern the same Boltzmann physics, right? And so the opening and closing of the ion channels is governed by the same kind of Boltzmann distributions, exponential distributions of conductances as a function of, in this case, memory potential. And so you have these beautiful physical analogs that can be exploited for building circuits that directly emulate the biophysics of computation with equal efficiency, thermodynamic efficiency in their computation. That's down here to femto, from femtoamps to higher nanoamps of currents for doing this computation innately. And so neuromorphic engineers have developed those systems, silicon retinas, right? So modeling, say, how the optic nerve works, right? And so there has been leverage to great efficiencies for not only computation, but also for, in this case, compression of information across the optic nerve. And here this allows to build systems, we call those dynamic vision sensors, that efficiently code events on the focal plane and then transmit those. Just only when something happens on the plane, then things are transmitted, and so that also saves tremendous energy. Right? So there's efficiency here in the representation that can be exploited owing to getting to the physical primitives of right. So implementing function natively, just at the in this case the pixel of each sensor here. And so this event-based representation has been harnessed for building large-scale reconfigurable neural systems that embed synaptic connectivity and plasticity, really owing to this event-based representations, right, in which that wires can be virtually made in efficient manner, instantiated dynamically in tables, in synaptic tables. So this way you can basically wire systems on the fly and implement synaptic connectivity and plasticity. And so just give a fast forward, because the field has been developed as chips. And so I just want to highlight a few important aspects of this, right? We can combine then the efficiency as well as the resilience of computation by really building systems that have a much better trade-off of machine complexity, the cost of computation, versus how hard it is, the task complexity. So as opposed to the traditional AI, this rule-based exact reasoning that implies at least a linear scaling in the implementation complexity, basically to search entire space in order to find a solution. So now approximate analog habitual / collective computation has much more favorable trade-offs that can be harnessed. And so in order to harness those efficiencies, it's important to consider both, I mean, so in terms of energy per task, it needs to be minimized. I consider that this really partitioned in energy per operation versus operations per task. And so algorithmic advances can really get down to lower operations per task, right? But equally important are device level improvements in lowering the energy per operation. So down to femtojoules per synaptic operation, owing to really advances then in the silicon integrated nanotechnologies, right? Devices that really operate at fundamental limits of efficiency. And that's where the connection between energy efficiency and performance link in, right? So you can really get great advances in the efficiency of compute by really shrinking the devices and lowering their energy. But then it's important to also consider advances in neuroscience / cognitive science, right? Computer science, in order to really make those systems then robust at the architectural and algorithmic levels. And so here's, so neuromorphic computing has been really harnessing those two aspects. And here's a state-of-the-art kind of overview of systems. Let me just highlight that. So now most of the systems, whether digital as in the third, in the three first columns here, or more analog systems as in the last three columns here, they're now all hovering around efficiencies in terms of joules per synaptic event that are in the order of tens of picojoules. And so that's great, but so again, so that's not quite as good as what is happening in the human brain, and for that matter, very far away from the Landauer limit, right? So how do you get closer to this greater efficiencies? And so it's important to consider two aspects. So one is better connectivity and long-range connectivity, because the brains are small word entities. And so neurons can connect very far, but they need to do so in such a way that they only have a few hops to the architecture to reach almost any place in the brain. And so a tree-based architecture is very important for that, while still You need to have arbitrary connectivity where you need to organize your, right? You can just have a pure tree. You also need to have this level of arbitrary connections. And so the hierarchical address event routing is then a means for doing this efficiently. Just highlighting, basically, you can have this hierarchies of assemblies where at the leaf node in our hierarchy, you have this full or sparse connectivity, but still quite fuller than at the whole plane level, right? Where you have this efficient integrated file rate receivers that do this local computation of synaptic transmission while having local tables that implement the connectivity. And at the higher levels in your architecture, you have progressively, I guess, higher level connectivity implemented by this tree-based architecture of routing nodes. And so the bottom line here is that you can get full range connectivity, arbitrary connectivity in a network, but still you get about 20 picojoule of energy per synaptic event, mostly limited by the interconnectivity. The fact that you still have to go off chip in order to get your connections implemented. And that's what really is the killer here, right? Because every synapse is only activated once, and you can use it just once every neuron spikes, obviously. And so you can't really recycle that unlike a convolutional neural network, which is really a contrived type of model, which doesn't really apply to whole brain computation. Right, you can't really recycle or reuse memory on a large scale. And so emerging memory technologies allow to directly couple memory and compute innately at the single bit or at the memory level, right? So we're now rather the word line that normally just drives a digital memory can now dub as your presynaptic action potential that drives a postsynaptic membrane conductance, right, on the bit line. And so this compute element has developed by this billion-dollar industry for emerging computation, emerging memories, such as random access, RRAM, right? So resistive random access memory, or PCRAM, right? Phase change memory, and all this, or magnetic RAM, all these different technologies that are physical conductance based, it can really be harnessed for doing innate neuromorphic computation and computing all on the same substrate. And so crossbar arrays of those elements have been harnessed for implementing synapse arrays, which then can be coupled with those integrated fire array transceivers, as I just showed, right, at coarser scale, and where then the compute, the neurons, with this IFI integrated fire array transceivers, then directly coupled to synapses, right, in a very efficient manner, right? It's tightly coupled in this architecture, vertically coupled in this architecture. So you have a direct connection between synapses and neurons here for high efficiently leaf node interconnectivity, while still having the global interconnect through this integrated fire array transceivers, which can have this addresses in and addresses out to this address event representation. So that's where, and so we developed a system like that in CMOS RM technology, right? Again, coupling neurons and synapses in this, here you have an array of 256 by 256 synapses coupled with an embedded array of 16 by 16 neurons, so implementing a basically a 256 by 256 transceiver, neuron transceiver that can go both ways. So you can have connections, inputs vertically and outputs horizontally, or you can transpose the connectivity in your architecture to basically implement recurrent connections efficiently, as well as implementing variational autoencoders or restricted Boltzmann machines by this transposing the direction of your connectivity in your array. And this is a way not only do you have very efficient computation, down to femtojoules per synaptic operation now, but further you can do this new types of, or this emerging types of generative models, such as variational autoencoders directly implemented in silicon innately using those resistive RAM devices coupled with CMOS at great efficiency. And here's a demonstration of how that is working. So here, let's say you have this picture of a 6, you perturb the pixels, right? And so that's now right, and you let now the system both recover so recognize the 6, and then also then recover it, basically by having this forward and backward inference and generation that can go hand in hand in this the Boltz machine. And so this is all done at energy much lower than a digital compute operation. Right, and so you can take this to the extreme. So we're now developing also this interfaces with high boundary memory and FPGAs on a larger scale for now up to 160 million neurons and 40 billion synapses. Right, we have this architectures, these trees of processing nodes, where each processing nodes have this efficient coupling between memory and compute. And then you have this also efficient long-range connectivity implemented with this hierarchical trees for doing this long-range computation. And so we'll take this again to Telluride this summer and just have fun with it. So I mentioned, so I can get this extreme efficiency. Well, I can get even further efficiencies by doing by recycling energy. So rather than doing resistive RAM or PC RAM resistive memories, if you have capacitive memories implementing this crossbar arrays, you can even get higher efficiencies by actually recycling the CV squared energy that is implied in the computation by coupling the electrostatic energy to inductive, because energy outside with a tank at resonance with the array. And this way we're being able to achieve about, because by this at resonance, we're able to achieve basically this efficiencies of about a femtojoule per kinetic operation, which is much better than what can be done today. And even so, with emerging technologies, we can even get down to the attojoule range of efficiencies. But that's work in progress. I'll stop there. So this basically means for, I should mention, so this can also be harnessed for this extreme efficiency can be harnessed into coupling also two brains in real time and this adaptive types of interfaces between brains and machines that not only get, you can get at the function of the nervous system, but also speak the same language of the brain, and then have this efficiency that can help to build the systems that can really this interface at massive scale. And I'll end here.
Okay, thanks for a great talk. We do have time for one question. So if you have a question, feel free to type in the chat or raise your hand. So maybe I'll start by asking the implication of this to the software. So when I was looking at the event cameras with dynamic vision sensors, my impression is that they would require different computer vision algorithms. And so in general, neuromorphic computing seems to be introducing a new paradigm for processing. And so I was wondering if you could comment a bit on its implication on the software, whether it could be compatible with existing things. If not, what do we do about the software?
That's a great question. So we have this software environment here, right, where software is really key here to make those systems not only efficient, but also functionally versatile. And so there's an entire software environment so in fact, as Emre Nefzi spoke earlier today, developed those software interfaces to this neuromorphic compute architectures that can then be coupled to this compute environments. And so we're working hard towards mapping. So have the software environment, right, that will be transparent to the user. So the hardware will be transparent, where then PyTorch and other frameworks can be directly mapped onto this architecture for doing this efficient compute. And so yes, so clearly software is actually, it's important to have those advances go hand in hand with the hardware developments for the community to make progress, because after all, it's really the applications that require the software interfaces to leverage that efficiency actually in the real world.
Yeah, okay. Thank you very much for the talk. And feel free to stay in case there are questions in the chat. Otherwise, thanks very much for the talk. And we're going to move to the second talk in the session, which is going to be delivered by Professor Cecilia Metra, who is a full professor at University of Bologna at Italy, where she has worked since 1991. She is an IEEE fellow and is the president of the IEEE Computer Society in 2019. Her research area is all things related to devices and circuits, and especially from the robustness and fault tolerance aspect. And today she's going to tell us about circuit level challenges and solutions for safe and reliable intelligent systems. Looking forward to it.
Okay, thank you very much. Thanks a lot, Professor Zhu, for the introduction, and thanks a lot to both you and Professor Panda for the invitation. So it's my great pleasure to deliver this presentation on the workshop on robustness and safe software, and we'll talk about the circuit level challenges and possible solutions for reliable and intelligent systems. So today we are thinking or hoping, let's say, that everything can become smart and intelligent. So we talk a lot about smart things, smart environments, smart homes, smart driving, smart industry, and all of this thanks to the widespread adoption of AI. And this, let's say, massive adoption of the AI is possible nowadays thanks to the huge amount of data that are generated by IoT. And we are talking every day about the generation every day of 4 terabytes of data. These are the amount of data to the connected vehicles. And these predictions, at least, are that by 2025, we will have 463 exabytes of data generated every day. And
on the other side,
Sorry, Kevin, I don't know if you are on the second slide, but we're still seeing the title slide.
Oh, it's interesting. I'm sharing that one right now. Can you see what's going on?
So what I'm seeing is the title slide.
Let me stop share and share again. Let's see whether that solved the problem. Maybe let me share this one. Can you see my screen now?
Yeah, I can see the screen. It's not in the presentation mode yet.
Okay.
But so
is that in the presentation mode?
Yeah. So, but we're on the title slide.
Is that on the first page?
Yeah. Okay. Right now.
Okay. I think I changed the maybe share the application does not really work well. Let's share the screen right now. So everything's fine, right?
Yeah.
Yeah. Sorry for the interruption. And so I'm talking about everything goes up, not the gas price, or not only the gas price, but also, for us, what matters is the data volume everywhere, right? The data coming from the email, from the camera, and all those data will push and give us a higher pressure for analyze them at the runtime and to deliver the in-time response of that. And not only that, but also the algorithms to analyze those data. If you look at the bottom right figure, it summarizes trend of the model size and the computation cost of those AI models in training. And the bottom gray curve is so-called the Morsnor 2x per 2 years. But if you look at all the other models from computer vision to the recent transformers and also the speech and other ones, they grow up dramatically faster than what the hardware can deliver in the traditional conventional fashion of that. So from both ends, we have much more data to analyze. And the model also, we need to work on those models and make those models even more efficient on the hardware by themselves. And if you look at our hardware itself, it actually has some dramatic problem, also called the von Neumann architecture problem. And in this architecture, if you look at the left side, there's a sort of a partition of the arithmetic circuits and also the cache and memory into a separate fashion of that. It helps the hardware efficiency in the past. But now, if you look at all those algorithms running on our hardware, right, the memory or the data movement really dominates all the energy consumption and latency through the entire one. Now, one example, as right plot shows, the memory will be the several orders of magnitude higher than the computer itself. And another example is the recent 500-watt release from NVIDIA of their processor. And only 40% of the energy is consumed by the computing. 60% is on different levels of interconnection from on-chip to chip, or the chiplet part of the consumption of that. So indeed, according to such an architecture today, and our dramatic bottleneck will be on the memory access themselves. It does not say like those people are not working hard and other people are working. If you look at this trend, the process goes up much faster, benefiting from the new devices and new architecture to deal with AI acceleration. And the bottom one is also the high-speed I/O, and they introduced new analog devices, and analog and the mixed signal design. And they also use the most advanced sort of a 3D packaging like the HBM, right? All this is a help to push up the performance of the interconnect bandwidth issues here. But nevertheless, the gap between the processing and the memory keeps going up. And this trend will eventually limit how much we can compute, not how much, how much computing power we can provide. So all those backgrounds drive the recent advance in one area called in-memory computing, as already addressed by previous speakers of Gert and Celicia. And this idea is really interesting because if you look at that one, traditionally we use the memory just to store the data, as the left plot shows here, right? So when you read, the weights are stored inside, and when you read, you row by row to fetch the data out, and then outside you have a digital computation engine like the PEs or the Max engine to compute the input and output together to get the final result. This is typical so-called MAC operation in the AI and consumes more than 70 or even sometimes 90% of the computation cost to process AI algorithms. And the new idea is actually to use the memory array itself as a computing engine. So in this case, the data actually becomes the control of which row you can open of that or on and off. And then when the data comes in through the word line, it mixed together with cell values, which is the pre-stored weights inside it. And then the output will be the automatically the multiplication and accumulation result coming from the bin line. And all those results will be computed in a massive parallel fashion. Now we activate all the memory cells at the same time. That's another important factor to push the energy efficiency in computing. And so by doing that, you have the right plot shows here, we can see that there's a dramatic improvement of the energy efficiency in AI computing. And it pushes up from a traditional processor with about 1 TOPS per watt into more than 100 TOPS per watt in today's silicon results from the in-memory computing test chips. And those are all for CMOS-based ones over there. And ideally, to make this one more efficient, we prefer all the weights will be stored on chip to minimize the data movement from layer to layer in the deep learning algorithms of that. But that also causes a problem in traditional SRAM-based in-memory computing because every SRAM cell itself is quite big for on-chip. It's fast, but it's big. You need at least 6 transistors or even more in the in-memory computing to take one cell, and each cell is just 1 bit over there. If you want to improve the precision, that's another problem in memory computing will be limited if we use CMOS of that. So considering all those advantages and disadvantages of CMOS-based in-memory computing and the non-volatile memory-based one, such as RAM-based in-memory computing, is a really exciting area to explore. In this case, instead of putting CMOS SRAM as a memory cell over here, we can use the RAM or other types like PCM on the cross point in the crossbar structure over there. And then the advantage of the RAM is that each one is non-volatile. So once you move the data inside with it, you don't have to move out in the in-memory computing. That's appropriate for the non-volatile memory of that. And you can also store that for a long time for edge computing and other purposes. And second one is that the NVM is also promising for multi-level or more multi-precision representation of the data of the weight inside. And that also is an advantage over the sort of a 1 bit per cell fashion in the SRAM design one of that. So those things will drive the research behind the RAM-based in-memory computing. But on the other side, we also need to be aware that those are new devices and new structures and new materials. They are not as stable as CMOS, which has been perfectionized for many generations of the technology here. So one common issue, as the right plot shows, is that those RAM devices will not be linear in the operation region. They may not be symmetrical when you program it up and down, and the program time is also be longer than the SRAM, although that factor has been solved and improved generation by generation for the RAM device engineering. And in addition, you're going to have lots of variations, like even the data I just quickly show you, just for one measurement from one wafer, you will see lots of variations. If you want to program to the same value, they may not give you the same one as a response of that. So when you propagate those device issues into the circuits and into the algorithm, and one of the key things we'll observe is accuracy loss. And when you have the in-memory computing chip consists of the RAM devices, you will see that even for a simple task like MNIST, right, the accuracy will drop quite significantly. And how much is the degradation of that depends on the amount of variations you have, the on and off region, how many precisions you want to program the RAM, and other issues involved. And so that's the number one issue, because if we claim to use a new hardware platform for the AI, the accuracy is the number one concern for software people and algorithm developers to accept this idea. And if the plot really shows up, like the right plot showing here for MNIST for CIFAR 10, and the accuracy drops from like 95% or 90% down to 80% or 70%, and that's not acceptable by the algorithm community to use this hardware platform. And so that's the number one concern we have to solve as a community together to provide a new computing engine. Other issues involve architecture, as we are going to support a larger scale of the AI algorithms. As the scale goes up, the number of PEs and tiles will also go up. So eventually the interconnection will become a problem, how to connect those multi-tiles. And we're back to the same problem of the data movement. In this case, even if we can use in-memory computing for the entire chip or the entire system, then the data movement is not limited by the I/O across the memory and computing chip, but then the on-chip communication or the in-package communication will be a bottleneck, consumes more than 50% of the latency, as we see the examples here. So this is the architecture level issues we need to do more research down the road. So in this talk, I'm going to focus on the robustness of that, or the accuracy degradation. And we start from a realistic data connection from the real RM wafer at 65 nanometer to see how much variation is indeed over there, and what are the sort of first order issues versus secondary issues we need to solve. And on the solution side, we propose two steps. One with a pre-mapping. So before we do map the algorithm to the hardware, we need to improve the model stability and also bring the variation into the training procedure. And then lots of books already discussed about that. I think one of the novelties we talk about is to bring the stability of the AI algorithms as a possible knob to help improve the situation. Then after we map that one, we can do something more adaptive, and through the hardware and especially the hybrid structure between the SRAM and RRAM to do the sparse adaptation and finally recover 100% of the accuracy of that. And that's the talk I'm going to discuss in more details. And thanks, I would like to acknowledge all the collaborators from all the funding agencies and students. So this is the test chip, we collect the data from and fabricated by SUNY party. And this is a 65 nanometer 1T1R test chip using the sort of pretty popular, the hafnium oxide as a materials for the RM fabrication. And from the entire wafer, we can see that this is a wafer level variation map we can present. And for the high resistance state and low resistance state, they have different amount of variations. The HRS usually has a much larger amount of variations, we can see from that. And that also make it not a favorable state. So we try to, when we program this one and using the conductance from RM to represent the data, we prefer the low resistance state of that. And how many levels we can put it? Well, it depends on the variation amount, right? If given a limited range of off versus on, the more levels you want to partition, actually for each level, you're going to suffer a larger amount of variation. So there's a natural trade-off between the levels you want to represent the data versus the robustness of that. And limited, that's a natural limitation inherent to the RM device today. And from this data, we can see that we can comfortably put probably 8 or 10 levels of the variation of the data precision inside it. And that's a static variation, limited ones. And for the dynamic ones, like those retention issues over there, for this technology, it seems pretty stable. And they are under the shadow of the static variation themselves. So overall, we can use probably 30% as index as a wafer level variations. And then we can achieve up to 16 levels, but that's really a high end and high risk factor. More comfortable will be 8 to 10 levels of that. And to evaluate the impact of that, before we do anything of the hardware design, we need to evaluate the impact and do the sort of cross-layer evaluation. And for that, we develop a cross-layer benchmark tool called CIM. And this supports in-memory computing with CMOS or RM. It takes algorithm factor and device and structure factors into it. It also considers different levels of interconnection, such as a network on chip, network on package for the chiplet-based integration of that. The tool is released at GitHub as open source, and you're more than welcome to use it, and we'll appreciate your feedback of that. And by using this tool, we can check, how many, if we do any programming or if we do any reconfiguration of the hardware and device, how much we can achieve from the algorithm side, or if we do any tuning of the algorithm for the same task, and how much improvement and robustness we can sustain those algorithms under the variational device itself. So just quick result is that, if you don't do anything, just to do straightforward implementation of the algorithm mapped to the hardware for our 65 nanometer platform, we can see that the accuracy will degrade a lot as we are increasing the levels of the RM. So for the, again, as a given sort of the range of the on and off is given, the more you partition them into 2 levels, 4 levels, 8 levels, or 16 levels, then each level will suffer larger and larger variations underneath. And then that's the main reason the accuracy actually drops a lot with the increase of data precision. So that means it is not a sort of a straightforward answer to say high level is better or worse, right? In this case, if the variation is really dominant, the high level of data representation in the RM1 is actually a bad effect. On the energy side, ADC and other previous circuits will be more dominant, and the massive parallel computing of the RM and its energy efficiency meets the requirement. So the energy and latency are not really dominated by the crossbar itself, but by the peripheral circuits as another point for circuit people to improve and innovate. As we mentioned, lots of people have done the research in this domain, and they're looking into how do we do the sort of a device level improvement, like the read and verify process, and also do the other sort of a variation aware training. One unique properties we look into is so-called model stability, because for the training of the deep learning ones, the landscape actually have different contours and different shapes or different roughness, even from the same training procedure of that. And this roughness can be visualized doing a sort of a 2D or multiple dimensional visualization of the landscape. And at the end of the training, right, the result or the solution should be on the bottom of such a valley, which means that you're reaching the local minimum of that. But how about the shape of such a valley, right? Some models can be smoother, like the denseNet to the right, and we can look at the roughness score as a regression result of that landscape. But some models, like the ResNet 56 to the left, is much rougher, and we can visualize this one from this one, and numerically use the roughness score to check the point of that. The point is that more stable, a shallower and smoother valley around the local minimum will promise a better stability if there's any variation attack from the device side of that. And that's the selection criteria we can leverage to improve to reduce the accuracy degradation when we use the RM with variations to map the algorithm inside. And this is one actually interesting to see. And more interesting, we can see that, even given the similar sort of algorithm structure for similar tasks like CFAR10, if you reinitialize it and write again, you may end up with different local minimum, and different local minimum may have different qualities of the roughness and the stability of that. And stability is also connected to the accuracy of that. Usually, as this result shows here, right, a lower roughness score means a more stable valley around it. Actually, can also give you a better accuracy. That means you may select a better local minimum as others to stabilize your accuracy and converge even faster than that. So that's the one. Through the training, we can try multiple times or even develop a more systematic approach to select a more stable model for our point. Model pruning and quantization have different impact. To support efficient in-memory computing, we have to prune the model to lower precision and smaller size of that. When we prune the model, you actually reduce the redundancy inside the model, and that makes the model more unstable and maybe more inaccurate under a given level of variation inside. On the other side, quantization, or means lower precision of the model, actually will improve the accuracy, as those plots showing here. As we move from 32-bit to 8-bit, there's a significant improvement of the smoothness of the valley around the local minimum, as this plot shows here. And that also reflects into the accuracy improvement, because now with a lower level of precision, you actually have a larger noise margin to tolerate for each level. In a quick summary, this is approach our group is exploring. The first step is called pre-mapping. So we do the variation aware training as other groups is doing, and we try to improve the stability and the robustness of the algorithm before we transfer them to the hardware itself. And this is a statistical process. There's no guarantee how much improvement it can have. We're just doing our best over here. We can use the knowledge transfer model to train a student model and with the variation involved. And even for the variation, we can try scan different levels of the variation. So one interesting impact is that when people try to inject a variation into the training procedure to make the training process more tolerant to the variations, there's actually a tricky point is how much variation you want to inject. Intuitively, it just says, okay, I just use the same amount of variations as I can see from the hardware. But this result shows that that intuition may not be correct. When you inject the variation inside, on one side, it helps the training algorithm to be aware of the variation and try to smooth out the loss function. But on the other side, the more variation you inject, the more disturbance to the landscape. It may not be converged smoothly and give you even more fluctuation. So there's a plus and a minus when you inject a variation. If we scan the level of variation, right, we can see that actually there's some natural property of the algorithm itself and give you a best point. This value is usually smaller than the physical variation you can see from the device. And this is related to the algorithm property, not to the device itself. And as you can see here, if you do such an experiment and pick up the best variation in the training procedure, you can improve the accuracy by up to 19%, depending on the specific algorithm and specific task. Nevertheless, even when we do that, we're going to see some degradation of the accuracy through the statistical training with the variation. And if we want to promise and guarantee the variation, even finally on the hardware, right, we have to think something out of the box. So the way we are doing is to add an SRAM array, which is a small array in conjunction with the RM array itself. The RM will host the main model of it, but it has a degradation of the accuracy, no matter how you do in the training step of that. But SRAM, even it's larger, is precise. So we can do an ensemble of that one to make sure that your overall accuracy is good. So after we map the main model to the RM, we can do the post-mapping training of the SRAM only to recover the accuracy. And this one should be pretty promising to solve that one. As a result shows, right, if you do the quick software training of the SRAM only, which is a fast in write, fast in read, and that does not take too much time. And then this one can, driven by the accuracy loss by the RM, and compensate that. It takes a small area, like about 10 to 15% of that, and can speed up this recovery to the baseline, and which is also 12 to 150 times faster than the traditional hardware approach. You read every cell and recover it, right? This one does not need to do any read from the RM again after we map them to the hardware. And currently we just tap out a 65 nanometer test chip with the CMOS and the RM at different precision on the same chip to demonstrate this idea, and hope by the middle of the summer we can report some new results of that. So in summary, I hope I deliver the message that in-memory computing is a promising area for future larger scale AI computing, but meanwhile we have to solve some critical questions like the device variations and their impact on the accuracy loss before we can make it as a mature platform for AI computing of that. And other issues involve the ADC precision and cost, as well as interconnection. How do we leverage hierarchical interconnection from the on-chip and chipnet technology to make the interconnection even more efficient is one of the topics we need to solve before we have a larger scale solution of that. So that concludes the talk, and thanks for your attention.
Yeah, thanks for the talk. Do we have any questions? So we do have time for a question. If you have any questions, feel free to type in chat or just speak up. So I did have a question actually about sort of the scalability of the RM approach, where if your weights are sort of, it's inherently using kind of a weight stationary data flow. And so I was wondering if the model has lots of weights, do you really need a huge area? And so if so, how is that going to be kind of more scalable?
Yeah, that's a great question. Actually, that's one of the active topics we are looking into right now. We do believe, we do have to put everything on the chip, the same chip, right? But it does not mean a same chip. It can be a chipnet. With the chipnet technology we are doing right now, you can really have a larger scale, even a wafer scale process in front of you with low energy, sort of a low power interconnection across chipnets. I think that's the trend to go to make the processing larger and larger. I think that happens actually not only for RM, but also for the CMOS too. We basically expand the scale of the one to try our best to pre-store all the data as much as we can on the same chip.
Yeah, I think the triplet idea, the combination of that is an excellent idea. So thanks for the wonderful talk. If there are no other questions, we'll move to the the last session. which we're going to hear from three speakers from the industry. The first speaker is going to be Dr. Paul Waterman. So he runs the ARM machine learning research and is a research associate at Harvard University. His research interests include efficient algorithms, computer architecture, and circuits. And today, he's going to tell us about functional safety for ML systems. So Paul, looking forward to your talk.
All right, great. Thanks for the intro, Juhas. I thought this was a really interesting workshop this morning. So thanks for organising this, Juha and Priya. I think I have a hard stop, so I have to keep to time. I'm not going to ramble too much. However, this slide deck's fairly high level, not a ton of low level technical detail, but I guess I'm hoping I can give some industry perspective on some of these topics. And in industry, we tend to use the term functional safety of user, at least for the aspects that I'm going to talk about here. I guess it's not always the sexiest of topics, even in industry. So, but I think it's a pretty critical one. So I think this is worthy of your attention. I'll jump in. Yeah, so in terms of drivers for this sort of thing, or drivers for ML systems in general, there's a ton of stuff, but I'd say most branches of computing at this point have been impacted by machine learning to some extent, and some to the extent where I'd probably call those computing systems ML systems now. And there's sort of many modalities of data that we, would process in those ML systems. Some are shown here. However, I think probably in the embedded space, more of these ML systems are impacted by functional safety than you might imagine. Of course, things like automotive heavily drive functional safety, but there's a lot more than just automotive. So I think it's interesting to bear that in mind when we look at this. So then in terms of ML systems themselves, I'm differentiating here from more traditional computing systems, which might be slightly arbitrary, but bear with me. This is a perspective that my colleague Ian Bratt and I have sort of been thinking a lot about lately. Traditional CPU systems we tend to think of as being as computer architects, we think in terms of a stack. We tend to start with the architecture, but then we have some hardware implementation of the architecture, and then we have some compiler toolchain, and then we have the source code, which some programmer writes for some application. This is all pretty well established stack. So what changes for ML driven systems? Well, we can analyze it with the same framework, but there's some sticky bits. So architecture, what does architecture really mean for ML systems? Well, probably something like a traditional CPU ISA might be a target for an ML system. But in terms of describing machine learning workloads, that's pretty fine granularity, like a CPU machine instruction. So often we talk more in terms of operators tend to be bigger linear algebra operators. We need hardware implementations, and they can include traditional stuff, CPUs and GPUs, and they can also include more different looking things like neural processing units, or NPUs, and various flavors and derivatives of that. Of course, we still need a compiler. The compiler here is going to take the ML workload, usually some form of graph, and map that onto the architecture to ultimately run on the implementation. Finally, the source code is now represented by some kind of machine learning model and some data, and I guess some training recipe that's used to train the model on the data. So that part definitely looks a bit different, and this has been sort of referred to as software 2.0, so a new way of programming computers, essentially. And I think maybe overstating this a little, but I think we're definitely living through a new hardware, software system stack development. And in some areas, this is coming much more quickly than others. But I thought for this talk, I think it's particularly interesting to sort of have a look at this and have a think about how functional safety might factor into this ML system stack, because I think we're going to need it in many applications. So I'm going to sort of jump through the computer architecture stack and pass some comments on a few aspects. So firstly, in terms of architecture, well, architecture for ML, it can be challenging. I think if you look at the common way to program using machine learning, we tend to use these high-level ML frameworks. There's lots of them: TensorFlow, PyTorch, JAX, Onyx, all this stuff, and usually compose programs of operators, and there can be lots of them. So TensorFlow Lite, for instance, which is a sort of inference-oriented subset, contains 145 operators, but full fat TensorFlow has thousands of these things, and their proliferation is a challenge because we want hardware that works well to cover these workloads and use cases. We don't want to support thousands of operators. That would be a challenge. So something we have initiated at ARM is the Tensor Operator Set Architecture, or TOSA, and you can think of this a bit like a architecture specification for machine learning. So essentially what it is an IR, and what we do is we can take models from various framework dialects such as TensorFlow and lower those to the TOSA IR. And this is a useful IR because it encodes enough high-level semantics that we can efficiently map those operators onto the hardware, but it's not so high-level that we have lots of them. Then the idea is we can then sort of lower that eventually onto the target hardware, whether it's CPU or NPU. Basically, the idea with TOSA is to have a set of primitive operations which are finite, but through their combination, we can get sort of infinite set of functionality. So 67 operators, and using just those 67, we can lower pretty much all of the common TensorFlow inference operators that we see to this subset. And this allows us to something much easier to reason about the hardware level. This is open sourced, and you can go and have a look at this, and you can contribute and use it in your own work. But I'm going to come back in a minute, some comments on how this can impact functional safety. So next, we need a hardware implementation. We're moving down the stack. So even if we have something like TOSA, we need an implementation of that. I've worked a lot on neural processing units, NPUs. This is a sort of a really efficient way to run those machine learning inference workloads, especially. This works really well in embedded. Ethos U55 is sort of ARM's greatest NPU product that we're really proud of. I'm not actually going to talk much about NPU. In practice, a huge amount of real world ML still goes on more traditional compute platforms, CPU and GPU essentially. In terms of functional safety, ARM actually has for a long time has had a line of functional safety enabled IP called the AE line. So we have essentially all the building blocks here. So we have Cortex A78AE and the Mali G78AE and the ISP as well, C71AE. And the idea here is these are built on existing IPs, but they have extra features and extra EDA treatment so that they have extra functional safety considerations. And there's a nice blog I've linked here actually if you're interested more. I'll go through really quickly just to give you an idea of what this is. So firstly, for a CPU, well, the big thing with this CPU is actually has redundancy. It has dual core lockstep. So every CPU actually is composed of two CPUs, and they both execute the same instruction stream. And when an instruction is completed, they're compared between the two pipelines to check consistency before the instructions retired. So it's quite a brute force way of getting functional safety, but it works really well and it's very easy to reason about. And actually, we've been doing this for quite a few years now, and lately we have some interesting features. We can actually do what we call split lock, where we can actually expose those redundant cores to allow them to run more workloads if we want to. So we can, for two cores, we can get 1x throughput without any functional safety, or we can run them in lockstep and get half the throughput with functional safety, which is easy to reason about. So have other features as well, but that's the kind of thing that we do there. The GPU has similar features as well. One of the interesting things we do with the GPU is we actually can partition the GPU somewhat similar, but here we tend to partition it so that some parts of the workload that might be have real-time constraints or other functional safety requirements can actually be separated from other parts of the workload. And also, obviously, the image signal processor is a really important piece in the case of visual perception systems, because all the image data flows through it. So this is an area where we're really sort of introducing quite a few innovations, even down to the pixel level. We consider reliability on the sort of pixel level in this IP. So there's a lot going on in the compute there to guarantee functional safety. And it's not just the compute, right? You need everything else to build a chip as well. So you need, coherent mesh interconnects, you need memory management units, you need interrupt controllers. All this stuff has to be functionally safe. If there's any, any weak links, they will determine ultimately the functional safety of your system. So we've been developing this IP for quite a long time. It's widely used, not, as I said earlier, not only automotive, but in quite a few embedded applications. I think the interesting thing, and I'll come back to this later, is that it's not really, a lot of these hardware features are fairly passive, and it could be that we interact a lot more with these and use these features a lot more intelligently, I think. Okay, going to keep this moving. A few comments on compiler. ML compilers are a really challenging problem, as probably everyone's aware. From a hardware point of view, it's fairly straightforward to, instantiate hardware with lots of multiply accumulate units in the case of an MPU. But actually keeping those MAC units fed is pretty difficult, actually. And so, what starts out as a MAC problem quickly becomes a data movement problem as you add more MACs. And in practice, we see many systems limited by memory bandwidth or storage to some extent, and that's especially true in embedded. In the MPU case, we have an offline compiler for MPU called Vela. So this has actually got quite a lot of clever stuff in it. So actually we'll take ML inference graph and heavily optimize it for the target hardware. This is open source, so it actually includes a performance model as well. So you can download this compiler and try it on your models as well. So I can get into this, and in CPU case as well, we tend to have runtimes that map the model onto the hardware. But I think this is an area where we could actually consider functional safety and potentially incorporate that as part of the compiler. I think that's a really interesting notion, which I can come back to in a minute as well. Okay, and then sort of finally, left this last, but we come to the model. So this is the sort of part that we program. So there's a huge amount to say here around functional safety, and I guess my highest level remark would be that a lot of this stuff is very new. So where we're seeing, for instance, features in cars that use machine perception, they haven't been widely deployed for more than a few years. So I think in many cases we're really learning how to deal with these systems. It can be really challenging. A couple of things I wanted to comment on, some relating from our own work in the team. So the first one, so this slide is for some work in my ML research group. We work a lot on not only improving the hardware for ML workloads, but also we always see very big gains when we work with partners to optimize their models for the hardware specifically. So something we've invested a lot in is the model optimization side of things. And a tool that we use a lot is neural architecture search. And this work, this is some work we've done recently where we use neural architecture search to optimize models. And here we're actually targeting to design models that exploit the hardware decompression in our own NPUs. So our NPUs support compressed models, and they do the decompression on the fly in hardware. And we're actually able to design models that actually compress better and exploit that feature much better. So then in terms of model size and accuracy, we can design models in a sort of semi-automated way that achieve significant improvements in model size compared to previous work. However, this sort of work and this this direction in general of optimizing models heavily for the hardware has some potentially interesting implications in the real world. And there's been some work in particular from, I think, Google, where they actually looked at the impact of pruning models on performance of a model on, out of distribution data, for instance. And it seems like there's some significant and systematic impact there. So I think there's obviously an interesting trade-off between optimizing the model for better hardware performance and then sort of real world sort of accuracy performance as well. I think this is a really interesting area. Okay, and then this is kind of an old slide, but another, I think, important remark here is that actually neural networks themselves are fairly tolerant of errors in various ways. This is some work that I did quite a few years ago now, actually built a chip to analyze this and then did some simulation work as well. But it turns out, if while you're executing your inference graph, you have bit flips in various places, weights, activations, various types of data, actually doesn't necessarily break your model immediately. And it's possible that for some models you can tolerate, surprisingly large numbers of errors before you actually see any discernible impact, at least in the average case. And you see the different types of data have different impacts on that, and different parts of the model are also more or less susceptible. So I think this is an area where it's possible we don't have to be as strict with error protection methods, at least in the data plane. We probably do in the control plane, but in the data plane, there might be some freedom to analyze the areas of the model that are more tolerant to errors and make some trade-offs with sort of PPA performance to exploit that knowledge. So I think this is an old slide, but I think this is still a very relevant topic. I think this is an area worthy of more exploration. Okay, and then so in terms of functional safety, I think we are also starting to see a lot of interest being created around probabilistic machine learning. This is possibly slightly orthogonal, but I guess the point with probabilistic machine learning is that we want to design models that can give answers with some with some indication of certainty or confidence, where that indication of certainty is statistically realistic, let's say. And this has been a big topic for a long time, but I think interesting functional safety is really driving more research in industry around this. We've looked at this in my team, and I think the version of probabilistic machine learning, which is a big field that we like the most, is the Monte Carlo dropout technique, because this allows us to use fairly standard neural network architectures. Essentially, it works by taking a standard vanilla model and adding some statistical dropout, which essentially then at inference time, we sort of generate n copies of a standard model, each with a different set of dropout weights. And this allows us to build, when we combine that, we build a statistical view of any classification, which is, is meaningful. So we like this approach because we can actually run it on real hardware as opposed to some other probabilistic ML. But it's quite hard to study on the hardware in various ways because it's not really good support for running this in the frameworks, and also in terms of software runtimes as well. So we've recently actually open sourced Axolotl. This is a sort of open source framework to essentially play around with MC dropout. So you can take a standard model and apply MC dropout and then actually run it all the way on an A-class core. And we've looked at some use cases there that are driving probabilistic ML. So I think that's another area. Potentially probabilistic ML can also help with functional safety. Okay, so I'm a bit short on time, but I wanted to wrap up, and this is possibly a bit of a non sequitur, but I think just to recap and add some more comments, this is probably what ML systems look like, probably a similar stack to what we're used to. Of course, on the model and data side, in terms of functional safety, I think there's a huge amount going on here to really understand machine learning models, how we put bounds on their performance in the average sense, and in the worst case, also how we develop probabilistic ML, how we deal with things like adversarial attacks and all this kind of stuff. So there's a huge amount going on there. But it's interesting to me when this comes into contact with the hardware. The compiler is one of the interfaces there. I think a really interesting direction is how can we, start to think about exposing some of the knowledge we have, perhaps at the machine learning level, to the compiler. Maybe the compiler can make more intelligent decisions about how it uses some of those hardware features like redundancy in the CPU and like workload partitioning in the GPU, these types of things. I think that's a very interesting area. In terms of the hardware implementation, I feel like in industry, we kind of know a lot of the tricks that have been around for quite a while. There's things like redundancy, there's things like error correction. We can, make flip-flops more resilient to errors, all these kinds of things, but there's a PPA trade-off there. And I think we want to, make that trade-off intelligently to maximize functional safety in terms of, fit rates and all these things, but getting the best PPA. And I think probably the way we do that is to expose some of these hardware resilience features to a greater extent. And that's all I had. And thanks for your attention. If there's any questions, I'm happy to.
Yeah, all right. So thanks for the talk. I don't know if you have a hard stop, but we, if not, then we do have time for questions. And so from the audience, if you have any questions, feel free to speak up. But if not, I was actually quite curious. I mean, when the ML system is interfaced in an end-to-end application, let's say an ISP in the front end, how, I was wondering if you could comment a bit on how to explore, co-explore sort of the interaction between, the front end, an ISP, for instance, and an ML system in terms of functional safety.
Yeah, that's a great question. And the very front end of the ISP, there's a lot going on there. So they use, for things like automotive, they often use quite different color filter arrays, for instance. And then, as you well know, there's a lot of stuff going on there in terms of finding dead pixels and things like that. And actually what we do in the ARM ISP does a lot of stuff like that. So we actually, at the pixel level, try and figure out if there's issues with the sensor. And then we can actually tag those pixels and send them all the way through. So there's a lot going on there. I think in terms of co-design, this is a really ripe area, and I think there's a lot to consider there. Yeah.
Yeah. So we have one more question from Professor Chi Zhu in the audience. So Chi, you can just speak up.
So Paul, thanks for the very interesting talk. So I have a question on. So you mentioned quite a few different things, right? Probabilistic ML, and then also at hardware level and compiler level. So ultimately, I think, right, to see, let's see if we have some functional safety requirements at the system level. So what's your thoughts on how do we combine all those together? And if the safety requirement, right, is in sort of nature of we have to make sure certain functionality is safe to the degree of 10 to the power of negative like 12, right? How do we actually do this? What's your thoughts on this?
Yeah, that's a good question. For me, there's some methodology challenges currently. The way we design functionally safe systems in industry tends to be based around fairly coarse block level analysis. So it tends to be independent of the workload, for instance. That's how things are done. I think it's obviously not that intelligent. I think if we can have a methodology that's a bit more cognizant of realistic workloads, then I think, there's a lot more PPA we can bring back. I think that's what I'm trying to allude to here as well, is everything traditionally is quite compartmentalized. I think, functional safety is not just adding features to hardware like redundancy and ECC and things like that. There's potentially a lot more to it than that. For the most functionally safe critical applications, then yes, we have to design them in that sort of black box way. But I think for a lot of embedded devices, we can sort of start to break down some of the divisions between, let's say, the hardware and the compilers. And I think, the example that's interesting is things like our dual core lockstep CPUs. There's a lot of flexibility there in terms of when we run them in dual core lockstep and when we run them in split lock. So yeah, I think there's some methodology challenges in the industry to sort of address there, but there's also a huge amount of opportunity by looking across this stack. That's a good question.
Thank you.
All right, so thanks, Paul. And then we'll move on to the second talk in the session, and that's going to be from Dr. Vincent Lee, who is a research scientist at Reality Labs Research, part of Meta, I guess. And he is primarily interested in software hardware co-design and applied security and privacy for machine perception. And today he is going to tell us about concretizing machine perception, security, and privacy challenges. So Vincent, go ahead, and looking forward to talk.
Thank you for the invitation and the introduction. So today's talk is about building computing systems for autonomous driving vehicles. So in today's talk, I will share some data and findings we got from profiling our own autonomous vehicle products. And one of the key findings is that autonomous vehicle software exhibits a very long tail distribution of the end-to-end latency. And the long end-to-end latency is very harmful to the safety of autonomous vehicles. I will show that long tail latency distribution exists in every components of autonomous vehicle software. And I will take the localization module as an example to show the cause of latency variation and how we can utilize the latency variation to design accelerators. And finally, I will briefly talk about digital twin-based simulation for autonomous driving tests, which could improve the development and verification efficiency by moving the real-world tests into a virtual environment. So here is a little background. According to the Society of Automotive Engineers, autonomous driving is classified into six levels from level 0 to level 5. Level 0 has no autonomous driving ability, and the level 5 is with full autonomous driving ability. And other levels are somewhere in between. So nowadays, for level 4 autonomy, many robotic taxi fleets has been operating in America and China. And in China nowadays, almost all the newly made electrical cars are equipped with advanced driving assistance system. And today, some ADAS system even start to use LiDAR and can navigate automatically in very complex to highway and urban environments. Here is a historical analogy we made. We regard autonomous driving systems as the next generation smart platform. We take the smartphone, which is the last generation smart platform, as an analogy. So compare with mobile phone, one thing for sure is that there will be a rapid growth of the market size of autonomous vehicles. And also as the on-vehicle computing platform becomes more and more powerful, there will appear some killer applications for these smart vehicles. We think that autonomous driving is currently at the early stage if we compare with the mobile phone. So the development of the computing system is very critical for the future smart vehicles. The right-hand side figure is the system architecture of current on-vehicle computing systems. It consists of hardware platform, real-time operating systems, and autonomous driving software. The autonomous driving software is composed of sensing, perception, and decision-making module. The perception module usually fuses sensor data to calculate the ego vehicle's position, and also to calculate the position and speed of other vehicles and pedestrians. With the results of perception, the decision-making module will devise a safe and comfort path, and the control algorithm will drive the vehicle along the path. So for future on-vehicle computer system, it will need a more efficient computing platform to better support future workload, and will leave more computing rooms for the killer applications. Then this section, this section will show the on-vehicle computing system design of our autonomous vehicles. So when designing an on-vehicle computing system, a number of design constraints need to be considered. The first one is the end-to-end computing latency, which is the time for processing a sensor frame and generating the path and control command to the vehicle. The end-to-end latency is critical to the safety of autonomous vehicles, because latency determines the longest brake distance and also affects the control stability when the vehicle is driving at very high speed. Another consideration is throughput. It's the sensor frame. It's a sensor frame process per second, and the control commands sent to the vehicle per second. And the energy and the thermal dissipation are also considerations. The power consumption will affect the battery life, and the thermal dissipation affects the reliability of the system and the cost of the system. So if the vehicle equipped with cooling system, the cooling system will also waste extra power, and the cooling system is very expensive. Having these design considerations in mind, we design our on-vehicle computing system, and the table lists the algorithm used for perception, localization, and planning tasks. We use traditional stereo vision algorithm to estimate the depths, and use a deep neural network model to detect objects, and use a VIO and GPS for localization, and use MPC for planning and control. And the figure shows the task graph of our on-vehicle computing system. And based on our evaluation of power and latency on FPGA, GPU, and CPU, and also considering task level parallelism, we propose a system using FPGA, NVIDIA GPU, and Intel CPU. FPGA is used for the sensor interface logical design and for sensor synchronization and sensor pre-processing. And NVIDIA GPU is used for running perception model and estimates depths. And Intel CPU is used for localization, planning, and control. And more details can be found in the reference paper at the bottom of this page. So here is the evaluation results. The total computing system power is about 120 watts, and the average end-to-end latency is around 160 milliseconds. But there is a long tail latency distribution. The latency variance is caused not only by the software system, but also by the dynamic environment. For example, the latency variation of the localization algorithm is mostly caused by the rapidly changing environment. So next, I will use the design of localization accelerator as a case study to show how to deal with latency variation and how to utilize this latency variation. So here is a basic background of localization algorithm. The localization algorithm pipeline consists of two parts, the front end and the back end. The front end detects salient feature points from each images, and it uses spatial matching to get the depth of the 3D points that correspond to the detected image feature points. And it uses a sequence of temporal matching to estimate the camera pose. The backend takes the estimated feature map and pose from the front end, and then refine the features and poses using either a optimization algorithm or a common filter based method. Here is some profiling results. Based on the results, we have several findings. First, compared to the front end, the back end exhibits higher variations. And second, in the back end, the marginalization operation contributes the biggest variation. And lastly, the latency of back end is correlated to the number of checked features in the environment. So it means that the latency variation of the back end algorithm is caused by the dynamic environment. So based on the previous findings, we find that the front-end hardware does not need to deal with latency variation. So here is the front-end hardware architecture. The pipeline, the hardware pipeline and on-chip memory microarchitectures are carefully designed, which guarantee the front-end hardware can receive high frame rate images. The high frame rate images can enable high performance temporal tracking and will give better front end results. For the back-end hardware design, there are two challenges. The first one is that as the back-end optimization algorithm is complicated and irregular, manually exploring the design space to get an optimal solution is very difficult. So we need a design tool to help with the design space exploration and hardware design optimization. The second challenge is runtime adaptation to the environment. Since autonomous vehicles typically operates in dynamic environments, which will affect the workload and runtime, and will give rise to latency variation. But a static hardware accelerated design usually considers the worst case, which will result in wasteful computation. So the design problem is whether we can use this workload variation to optimize the hardware design at runtime. To overcome the challenges, we propose a design framework. First, the framework uses macro data flow graph to simplify the design space exploration and used to represent the algorithm. Then based on the data flow graph and our domain knowledge, we design a hardware template. The hardware template has several customizable blocks whose power and latency can be tuned through a number of parameters. Next, given the design constraints and parameters in the hardware template, a constraint optimization problem is formulated. And an optimal design point can be obtained by solving the optimization problem. Then we get an optimized static design. At runtime, the framework can close some hardware blocks through clock gating to reduce power according to the workload variation, while not affecting the accuracy and the latency of the hardware. And here is a detailed design of the framework. The above figure is the hardware template. In the templates, the Schur component and the Cholesky decomposition component are customizable blocks. And the formula shows the optimization problems we formulated. And these parameters are the number of computing units in these customizable blocks. the right figure explains why the runtime optimization can work. The reason is that the static design always accommodates the largest number of iterations to guarantee the accuracy for the worst case. But at runtime, the iteration number can be decreased for those non-worst cases. So the customizable block can close some computing unit to save power while meeting the latency requirements. So here is the evaluation results. The left figure demonstrates the effectiveness of the static optimizer. The results shows that automatic synthesized designs are optimal designs. The right figure shows that compared with Intel and ARM processor, our accelerator design can greatly improve performance and reduce power consumption. And based on our evaluation, the runtime mechanism can save about 10 to 20% power consumption compared with the static design. The last part briefly introduce the digital twin-based simulator. So this page is about the simulation tool for testing and verifying autonomous driving software and hardware. So testing autonomous driving system is very expensive. Keep a number of autonomous vehicle running on the road is expensive. So if you want to test a highway scenario, you have to drive the car to the highway. And if you want to test or verify the software and the vehicle in the traffic jam scenario, you have to wait for the traffic jam. And also verifying the accuracy of the aforementioned localization hardware design also needs a large amount of data. Collecting these data from various environments is also very expensive. So we use a digital twin-based simulator to reduce the testing and the verification costs. The digital twin simulator includes a digital twin map and high fidelity sensors and vehicle models. And we built the digital twin map from the high definition map used by autonomous vehicles. And we use graphical engine to render sensor streams and use physical engine to simulate the vehicle movement and the interaction between traffics. So the simulator can generate sensor stream to the autonomous driving software, and the autonomous driving software generates send the control commands back to the simulated vehicles and to drive the simulated vehicles. So the system supports end-to-end algorithm test and also supports model and software and hardware testing in the loop. So based on our evaluation, so by putting a physical test into the virtual digital twin environments, the testing and the data collection costs can be greatly reduced. Okay, that's the end of my talk. Thank you much.
All right, thanks for the talk. So I wonder if there are any questions from the audience. We do have time for questions. Well, if not, I was quite curious about the simulation. So in the simulation, is there kind of a scalability issue as far as the number of vehicles and the scale of the city that you can simulate? Or I mean, in other words, how do you make the simulation more scalable?
Yes, I didn't touch the architecture of this digital twin simulator. The bottleneck of the simulation is the sensor module. It uses graphical engine to do the rendering, which is very computational expensive. So if we want to make a large scale simulation for autonomous driving, we need some kind of distributed system to distribute these sensor rendering to or offload this sensor rendering to to different node to make sure it can be scaled up.
Okay, yeah. So thanks for the talk. Well, are there any other questions? Well, if not, I guess we are about to wrap up. I don't know if we have Priya here. Actually, are you still here? Oh yeah, you are. Okay, great. So, well, I guess, so, I think we had a successful workshop, and thanks to all the speakers and the audience. We certainly had great fun organizing it and talking to you all. And the intention is to keep this going. We ran this the first time in ASPLOS 2021 last year, and so this is the second instantiation, and so hopefully we can keep this going. And so feel free to send us any feedbacks and comments, and the videos. So the video is going to be posted, and so except those who requested not to be recorded. So that's all from my side. Okay, so I guess that's it. And
thank you for organizing.
Thank you. Thank you, everybody.
Thanks. Bye, everybody.
Bye.
Bye.